Hello there, and welcome to Science for Sleep, where curiosity slows its pace and science takes its time to wander. Tonight, we set our sights on something that has been above us for as long as there have been eyes to look up. It is the vast band of light, faint yet unmistakable, stretching across the night sky. You've probably seen it on a clear night away from city lamps, a ghostly river of stars glimmering as if someone spilled light across the darkness. That is the Milky Way, the galaxy we call home. It is immense, intricate and quietly astonishing. But here you are, settled in this moment, and here I am, ready to guide you through it at a gentle pace, a pace that lets your thoughts soften while the universe quietly unfolds. Where are you listening from tonight? Is the sky above you clear or hidden by the glow of city streets? Maybe it's daytime where you are, and the stars wait patiently just out of sight. Perhaps you're indoors, lights dimmed, listening while you drift toward rest. No matter your setting, you share something with everyone who has ever lived. Every human being has looked up and wondered about the faint glow that arcs above. In every era, on every continent, that glow has been there, waiting. It connects us, even as the galaxy itself spins slowly, carrying us around in its immense arms. If you find comfort in this exploration, if it brings you a little peace or quiet wonder, I'd be grateful if you tapped the like button or subscribed. It helps this calm little corner of the internet reach others who may need a pause too. With that, let's take our first quiet step into the story of our galaxy. The Milky Way has been with us since long before we knew its true nature. To the naked eye, it doesn't immediately look like billions of stars. It looks more like a band of mist, a pale streak painted across the night. That mist fooled many generations. To the ancient Greeks, it was milk spilled across the heavens, the milk of Hera, the goddess, which is where the name Milky Way originates. Other cultures had their own explanations. Some saw it as a river, others as the path of spirits, or the road of animals moving across the sky. Without telescopes, without science as we know it, people used stories to give shape to the strange light. And those stories made sense in their time. After all, the Milky Way truly does look like a river, stretched thin and shining against the dark. The truth, of course, is that the Milky Way is not a river and not milk. It is our galaxy, a sprawling collection of stars, dust, gas and dark matter, bound together by gravity. It is vast beyond everyday comprehension. Our planet is just one small speck, orbiting a medium-sized star, tucked away in one of the spiral arms. If you could see the entire Milky Way from outside, it would appear as a great whirlpool of stars, graceful yet immense, spinning slowly over billions of years. But we cannot step outside. We live inside it, looking outward, trying to piece together what the whole must look like. That glowing band across the sky is the inside view. It's like trying to imagine the entire forest while standing in the middle of the trees. Imagine standing somewhere very dark, far from the haze of city lights. If you let your eyes adjust, you'll begin to notice that the faint stripe in the sky is not uniform. Some areas look brighter, crowded with more stars. Other regions appear dimmer, even cut through by dark lanes. Those lanes aren't empty. They're full of clouds of gas and dust so thick that the light of stars behind them cannot reach us directly. With the right instruments, we can peer through or around them, but to the eye they look like black gaps in the band of light. These dark regions puzzled observers for centuries. Some thought they were holes in the sky. Today we know they are the raw material for stars, the very stuff from which new suns are born. From Earth, we cannot see the entire Milky Way in one sweep. It's too vast. But over time, astronomers have mapped it, using not only visible light but also radio waves, infrared, X-rays, and more. Each wavelength reveals a different layer. Radio waves slip through the clouds, showing structures we cannot see otherwise. Infrared light highlights heat from stars hidden in dust. X-rays mark the presence of violent events, exploding stars or matter falling into black holes. Piece by piece we assemble a picture. The result is a galaxy about 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars, though the exact number is uncertain. Alongside them are planets, moons, asteroids, comets, nebulae, and vast invisible envelopes of dark matter. It's easy to feel small when thinking about numbers like that, but small doesn't mean insignificant. After all, you are part of this galaxy. Every breath you take contains oxygen forged in stars that lived and died long before the Earth formed. Every atom of calcium in your bones was built in the heart of a star. When you look up at the Milky Way, you're not just looking at your surroundings, you're looking at the family you belong to on a cosmic scale. What strikes many people when they first see the Milky Way in all its brightness is how alive it seems. The stars twinkle, the clouds stretch like brushstrokes, and the arc spans from horizon to horizon. It looks like something moving, something almost breathing. Yet the motion we see in real time is an illusion of scale. Stars do move. The entire galaxy rotates, with our solar system making a full orbit roughly every 225 to 250 million years. But compared to the length of a human life, that motion is glacial. The stars seem fixed, yet in truth they are in motion, each one pulled by gravity, each one tracing a path through space. That slow dance has been going on for billions of years. The Milky Way itself is thought to be about 13.6 billion years old, nearly as old as the universe itself. Over that time, it has grown by swallowing smaller galaxies, merging with them and adding their stars to its own. It will continue to change. In about 4 billion years, it will collide with the Andromeda galaxy, another spiral nearly as large. The two will merge, reshaping into something new. But for now, here we are, one of countless civilizations in countless galaxies, circling quietly inside this one. Astronomers have tried to give structure to our location. They describe the Milky Way as a barred spiral galaxy, with a central bar of stars stretching across the core, from which spiral arms extend. Our solar system lies about 27,000 light-years from the centre, nestled in a minor arm called the Orion Arm, or sometimes the Orion Spur. It's a quiet neighbourhood, not too close to the galactic centre, where stars crowd together and radiation is intense, and not too far out at the edge, where stars are sparse. We live in a zone that is, in a way, just right. For most of human history, though, none of this was known. For thousands of years, the Milky Way was only what could be seen with the naked eye. Galileo was among the first to aim a telescope at it in 1610. What he saw astonished him. The hazy glow resolved into countless individual stars, too many to count. That discovery changed everything. The Milky Way was no longer a mystery mist. It was a field of stars stretching far beyond what the eye could detect. From that point on, we knew the universe was larger than we had imagined, and yet even Galileo didn't grasp the full scale. It took centuries of careful observation, measurement and mathematics to understand the Milky Way as an entire galaxy. For a long time, many astronomers thought it was the whole universe. Only in the 20th century did we learn that there are countless galaxies beyond, each with billions of stars of its own. The Milky Way is just one among hundreds of billions in the observable universe. Still, for us, it is special, because it is home. As you think about that glowing arc across the night, you might wonder how many people right now are looking at it too. In remote deserts, on mountaintops, from ships at sea, there are eyes turned upward, tracing the same light. Some see it with awe, others with routine, perhaps some with superstition, but all see the same galaxy. Across cultures and centuries it has been a constant presence. It was there for ancient farmers measuring seasons, it was there for travellers using stars to guide their journeys, it was there for dreamers wondering what lies beyond, and it is here now as you listen and slowly unwind, a companion in the night sky. The Milky Way is more than just stars. It is patterns of light and dark, places of creation and destruction, currents of gas flowing between arms, and magnetic fields threading through space. It is the backdrop of every night since Earth cooled enough for skies to clear. It is both familiar and strange. You live inside it, but you cannot see it whole. And that makes it all the more intriguing. To know the Milky Way is to accept that you are part of something far too large to fully grasp, and yet close enough to feel. And so, as we settle into this long journey together, we begin with that simple arc of light in the sky, a feature as old as humanity itself, a reminder that while our lives are brief, they are carried along by something vast and ancient, a structure that cradles stars and planets and all the stories we will ever tell. When you hear the phrase "a river of stars," it might sound like something too fanciful to be real, yet that is exactly what the Milky Way looks like to the human eye on a clear night. If you've been fortunate enough to step outside of the glow of cities, to stand in a place where the darkness of the sky is unbroken, then you may have seen it. The sight is unlike anything else. From one horizon to the other stretches a faint milky arc, its surface mottled, some parts brighter, some darker, filled with the shimmer of countless stars. It doesn't shine in the same way as the bright pinpricks of nearby stars. Instead, it glows, as if smeared into the sky, a soft band that gives the impression of a river slowly winding its way overhead. For many people in the modern world, this view is unfamiliar. Artificial lights, street lamps, billboards, and the glow of buildings have washed out much of the sky. In large cities, you might see a few dozen stars on a good night. The Milky Way itself is often invisible to the unaided eye. That wasn't always the case. For most of human history, the night sky was crowded with stars. The Milky Way was unavoidable, a presence that shaped stories, calendars, and navigation. People looked up and saw it night after night, the same way we see the moon or the sunrise. Today, it takes effort to find it. You have to leave behind the bright edges of civilization, drive into deserts, climb into mountains, or sail into seas. When you finally see it, the effect can be overwhelming. It's easy to understand why early civilizations imagined it as something supernatural. Standing under the Milky Way gives the same feeling as standing beside an immense river. The eye traces its curves, notices its swirls, sees how it thickens and fades. In places it appears dense, packed with countless points of light, while in other sections it seems broken, interrupted by dark patches. The effect is that of flowing motion, though the stars are not rushing past like water. The impression comes from scale and structure, from the way billions of distant suns blend into a band that resembles a current. The name Milky Way comes from ancient Greece, but other cultures gave it other names, many of them connected to water or pathways. In China, it was called the Silver River. In parts of Africa, it was the backbone of night. In Finland, it was known as the pathway of birds. To the Inca, it was the celestial river, a reflection of rivers on Earth. The similarities between so many names reveal how people across the globe perceived it in much the same way, as a river or a road stretching across the heavens. The reason it looks that way has to do with our vantage point. The Milky Way is a disc-shaped galaxy. Its stars are spread out in a flat plain, like a vast whirlpool. Because we live inside that disk, when we look across it, our line of sight passes through an enormous number of stars. In directions away from the disk, the stars thin out and the sky looks sparse. But along the plane of the galaxy, the stars stack up, creating the glowing band. We are looking edge-on through the crowded centre of our galactic disk. It's similar to standing inside a forest. If you look up, you see sky between the branches. If you look sideways, you see trees upon trees stretching into the distance, appearing dense and impenetrable. The Milky Way's band is the sideways view of the galactic forest. With the naked eye, you see only the brighter parts of this structure. A camera set on a long exposure, however, reveals more. Photographs taken from dark places show a sky alive with colour and complexity. Reds and pinks mark clouds of glowing hydrogen gas, places where stars are forming. Blue wisps trace reflection nebulae, clouds of dust reflecting the light of nearby stars. Dark lanes snake across the band, blocking light from behind. Modern images bring out vivid hues and details, but the basic view, the glowing arc, is what people have seen for millennia. The darker regions often look like gaps, as though stars are missing, but they are anything but empty. These areas are filled with cold gas and fine dust. The material is thin compared to air, yet across light years it accumulates enough to obscure distant light. Astronomers call these regions molecular clouds. They are the raw ingredients of stars. Within them, gravity gathers matter into dense clumps. Over millions of years, those clumps collapse until nuclear fusion ignites, and a new star is born. So the dark gaps in the Milky Way, the places that look like empty rivers running through the band, are actually nurseries, the places where the next generation of stars is slowly gathering itself together. To the eye, they look like voids. In truth, they are among the busiest parts of the galaxy. Busy not with movement we can see, but with processes unfolding across unimaginable timescales. It's worth remembering that everything we see in the Milky Way is light that has travelled for years, centuries, or even millennia before reaching us. The stars we see at night are not as they are now, but as they were when their light left them. The brighter stars in the band may be dozens or hundreds of light years away. The more distant clouds can be thousands of light years away. To look at the Milky Way is to look into history, a view across time as well as space. That river of stars is not only stretched across the sky, it is stretched across the ages, carrying us into the past every time we lift our eyes. The psychological effect of seeing the Milky Way clearly is hard to overstate. Many people who encounter it for the first time describe the experience as disorienting, humbling, or even emotional. Some feel small, confronted by the scale. Others feel a sense of belonging, recognizing that Earth is not separate but part of this larger structure. Ancient people had similar reactions, though they expressed them in myths and rituals. They built stories into the band of light, seeing it as the path of gods, or the road souls take after death. In some traditions, the Milky Way was seen as the ashes of a great fire. In others, it was the dust of travellers. These interpretations, though varied, all treat the Milky Way as something significant, something more than just a streak in the night. Astronomers eventually revealed the true explanation, but that hasn't diminished the wonder. Knowing that the Milky Way is billions of stars does not make it less impressive. If anything, it makes it more so. The idea that each faint speck is a sun, many with planets, some with worlds that may resemble our own, deepens the sense of awe. That river of stars becomes not just light, but the collective glow of billions of potential solar systems. In practical terms, the Milky Way has also been useful. For ancient navigators, it was a guide. Sailors on open seas, long before compasses, used the band as a reference, tracing their bearings by its curve. On land, nomadic peoples align their travels with its arc. Even without understanding its true nature, they recognized its consistency. It rose in the same place, set in the same place, and offered a map that stretched across the sky. Its reliability made it a companion as well as a mystery. There is another reason the Milky Way is called a river. It is not only a band of light, it flows. Not quickly, not in a way you notice in a single night, but across years the stars shift. The Earth spins, orbits the Sun, and the galaxy itself rotates. The band changes position with the seasons. In one part of the year, you see the brighter regions where the galactic centre is visible. In another, you see the sparser regions, where we look outward toward the thinner edges. This rhythm has been part of human calendars for as long as we've been measuring time. The Milky Way is not fixed. It has its cycles, and we, without realizing it, are carried along with them. Modern science has given us ways to measure those motions. Astronomers track the positions of stars, noticing tiny shifts over decades. These shifts confirm that the stars are not static but drifting, each following its orbit around the centre. From within, the Milky Way seems eternal. From a scientific view, it is dynamic, a system in constant motion. The river flows not only in appearance but in fact. Its stars, its gas, even its dark matter are all moving, bound together in a dance orchestrated by gravity. The scale of the Milky Way is beyond direct experience. The band across the night is only a glimpse of it, a slice seen from within. Our galaxy is about 100,000 light-years wide. Light, the fastest thing in the universe, would take 100,000 years to cross from one side to the other. Yet to the naked eye, all of that appears as a hazy streak. We see only the combined glow of the nearest parts. It's like standing beside a vast ocean and seeing only the waves breaking on shore, never the full expanse beyond the horizon. Despite this limitation, our ancestors gave names to the brighter and darker parts, described constellations along its length, and wove it into their daily lives. They did not need to know about dark matter or galactic rotation to recognize that the Milky Way was central. Today, we can measure, map, and model, but the essential experience remains the same. You stand under the night sky, let your eyes adjust, and there it is, a river of stars flowing overhead. And while it is a sight that belongs to the past and the present, it also points toward the future. That same band will be visible long after we're gone. It will outlast civilizations, languages, and even continents. Long after every human life today has ended, the Milky Way will continue to glow, carrying the record of our existence along with billions of other stars. It is a reminder of continuity, of something steady against the backdrop of change. As we continue exploring this galaxy we call home, that river of stars will remain our reference point. It is our direct, visible connection to the structure we live inside. Whether seen with the naked eye or through the lens of a telescope, it is the starting place for understanding the Milky Way. Not an abstract map, not a computer model, but the actual sight of our galaxy stretched across the night, present to anyone who takes the time to look. When people hear the name Milky Way, they often imagine only the pale band of light across the night sky. That view is part of it, but it's not the whole. The Milky Way is not just a streak overhead, not only the shimmer of countless stars blending together. It is an entire galaxy, and that word carries with it a scale that can be difficult to take in. To understand what the Milky Way truly is, we have to look past the glow and begin to picture its full shape, its components, and the way it fits into the larger universe. A galaxy is a vast system of stars, gas, dust, and dark matter, all bound together by gravity. The Milky Way is one such system, a barred spiral galaxy with a disk that stretches about 100,000 light-years across. To put that in perspective, light travels almost 300,000 kilometers in a single second. In 1 year, it covers nearly 9.5 trillion kilometers. Multiply that distance by 100,000, and you arrive at the width of our galaxy. It is almost impossible to grasp such a distance, because there is nothing in our daily lives to compare it to. Earth itself is just over 12,700 kilometers wide. Even the orbit of Neptune, the outermost planet of our solar system, is only about 4.5 billion kilometers from the Sun. All of that is a tiny dot when compared to the span of the Milky Way. Inside this vast disk are somewhere between 100 billion and 400 billion stars. The range exists because counting stars is not simple. Many are faint, hidden by dust or lost in the crowd. Some are too small and dim to be seen even with telescopes, while others shine brightly enough to be visible to the unaided eye. Alongside these stars are planets, moons, comets, and asteroids, numbering in the trillions. Our solar system is just one among countless others, orbiting quietly within a minor spiral arm. When you look up at the night sky and see a handful of stars, remember that they are only the closest and brightest, a thin sampling of the vast population spread throughout the galaxy. The Milky Way has structure. It is not a random scatter of stars. Astronomers describe it as having several key parts. There is the disk, a flat, rotating region where most of the stars and gas reside. Within the disk are spiral arms, regions where stars are more densely clustered, winding out from the centre. At the heart of the disk is the bulge, a thicker, rounder collection of stars surrounding the core. Beyond the disk lies the halo, a sparse sphere of older stars and dark matter that envelops the entire galaxy. Each of these regions plays a role in shaping the whole. The spiral arms are among the most recognisable features, even though we cannot see them directly from our vantage point inside. By mapping the positions of stars, nebulae and star-forming regions, astronomers have traced the pattern. The Milky Way has a central bar of stars, and from the ends of this bar, spiral arms curl outward. These arms are not solid structures. They are more like traffic patterns, places where matter bunches up as stars orbit the centre. In these regions, gas clouds are compressed, leading to the birth of new stars. That is why spiral arms glow more brightly than the spaces between them. They are stellar nurseries, crowded with young, hot, luminous stars that shine intensely before fading in relatively short lifespans. Our own solar system resides in a minor spur between two larger arms, a quieter location that offers a stable environment for life to develop. The bulge at the centre of the Milky Way is a dense, crowded region of stars. Unlike the spiral arms, which are rich in young blue stars, the bulge is filled mostly with older, redder ones. At the very centre of this bulge lies Sagittarius A, a supermassive black hole with a mass of about 4 million suns. It cannot be seen directly, but its presence is known through the orbits of nearby stars, which whip around an invisible point with extraordinary speed. This central black hole anchors the galaxy, its gravity shaping the motion of stars near the core. While it is not actively devouring large amounts of matter at the moment, it occasionally flares as gas and dust fall into it, releasing bursts of energy detectable from Earth. Surrounding the disk is the halo, a vast diffuse region extending far beyond the visible edge of the galaxy. The halo contains ancient stars and globular clusters, which are spherical groups of tens of thousands to millions of stars bound tightly together. These clusters are some of the oldest structures in the galaxy, with ages exceeding 10 billion years. They are fossils of an earlier time, remnants from the Milky Way's youth. But the halo is dominated not by visible stars, but by something far more mysterious: dark matter. Though we cannot see it, measurements of the way stars orbit the galaxy reveal that there must be far more mass than what is visible. The outer stars move too quickly to be held by the gravity of the stars and gas alone. Something unseen provides the extra pull, and that something is called dark matter. By current estimates, dark matter makes up about 85% of the galaxy's mass. Without it, the Milky Way would fly apart. The gas and dust in the Milky Way are as important as the stars. They make up what astronomers call the interstellar medium, the thin mixture that fills the space between stars. Though tenuous compared to air, it stretches across light years, creating clouds that can block or reflect light, absorb radiation, and provide the material for new stars. The cycle of the galaxy depends on this medium. Stars form from clouds, live their lives, and eventually return material when they die. Supernova explosions scatter heavy elements, enriching the gas with carbon, oxygen, and iron. Those elements then gather into new generations of stars and planets. Without this recycling, the galaxy would long ago have exhausted its supply of gas. Instead, it continues to produce stars, a process that has gone on for billions of years and will continue for billions more. If you picture the Milky Way as a whole, imagine a flat disk with graceful spiral arms, a bright bulge at the centre, and a faint halo extending outward. Now imagine that disk rotating. The stars orbit the centre, each at its own distance, completing one revolution over hundreds of millions of years. Our Sun, along with Earth and the other planets, takes about 225 million years to circle the galaxy once. That means that since the dinosaurs roamed Earth, the solar system has made only one orbit. In its lifetime, the Sun will complete perhaps 20 orbits before it dies. The galaxy's motion is slow from our perspective, but relentless over cosmic timescales. One of the most surprising aspects of the Milky Way is that we cannot step outside it to take a picture. Every image you've ever seen of the Milky Way from the outside is either an artist's rendering or a photograph of another spiral galaxy meant to serve as an example. Our vantage point is from within, looking outward through the disk. It is like trying to describe the shape of your own house while standing inside one of its rooms. Only by measuring distances, plotting positions and comparing observations can astronomers reconstruct the whole. The view we see in the night sky is only a slice, but careful mapping allows us to imagine the entire structure. The Milky Way is not isolated. It is part of a collection called the Local Group, a cluster of more than 50 galaxies bound together by gravity. Among them, the largest are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. The rest are smaller dwarfs, some orbiting close to the larger ones. These neighbours interact, exchanging stars, pulling on each other with tidal forces and occasionally merging. The Milky Way itself has consumed smaller galaxies in the past, and streams of stars still stretch across the sky, remnants of those mergers. The galaxy we see today is not the one that existed billions of years ago. It is the result of growth, collisions, and constant evolution. So what exactly is the Milky Way? It is a vast barred spiral galaxy, nearly 100,000 light-years across, containing hundreds of billions of stars, planets, and clouds of gas, all wrapped in a halo of dark matter. It is ancient, more than 13 billion years old, yet still alive with star formation. It is structured into arms, bulge, disk, and halo, each contributing to the whole. It is dynamic, rotating and changing, a system in motion. It is part of a larger group, influenced by neighbours, destined to one day merge with Andromeda. It is both familiar and mysterious, a home we know in part but cannot fully see. When you look at the faint band across the night sky, you're looking through one layer of this structure. You're seeing stars in the disk, dust clouds, and glimpses of distant regions. Beyond that visible glow lies the bulge, the halo, the bar, and the dark matter that binds it all together. Every star you see is part of this system. Every planet orbiting those stars belongs to the Milky Way. Every comet, every cluster, every nebula is another piece, and you, listening here, are a part of it too. The atoms in your body were made in its stars. The light that reaches your eyes has crossed its vastness. To ask what the Milky Way is to ask what your larger home is, the context in which all of human history has unfolded. And while this picture may sound complete, it is not final. Much about the Milky Way remains uncertain. The exact number of stars is not known. The detailed shape of its arms is still being refined. The nature of dark matter remains elusive. Each new telescope adds detail, sharpens the image, and sometimes changes the story. The Milky Way is not only a galaxy, it is also an ongoing investigation, a puzzle we continue to piece together. Every observation adds another layer, another way to understand the place we inhabit. From this perspective, the Milky Way is not just an object in space, it is a framework for life and thought. It is the backdrop to every night sky, the container of all our history, the source of the elements that make us. It is our home galaxy, and while there are many galaxies, for us there is only one that matters most because it is ours. Long before telescopes, long before astronomers began measuring the heavens with mathematics and instruments, the Milky Way was already a part of human life. It was there every night, arcing overhead, too prominent to ignore and too strange to leave unexplained. People looked up and searched for meaning in that band of light. They had no way of knowing it was billions of stars, but they had imagination, and imagination filled the sky with stories. For early civilizations, the night sky was not just decoration. It was a calendar, a compass, a clock, and a storybook, all in one. The stars marked the seasons, guided journeys across deserts and seas, and became the backdrop for myths and legends that explained both the world above and the world below. The Milky Way, brighter than any single constellation, demanded explanation. Its presence was constant, its form unmistakable. Wherever people lived under dark skies, they saw it, and they named it. In ancient Greece, it was said to be the milk of the goddess Hera spilled across the heavens. According to one version of the story, the infant Heracles, known later as Hercules, was brought to Hera to nurse, but Hera, not knowing who he was tricked into feeding him. As he drank, her divine milk spilled into the sky, forming the glowing band we see today. The very name Milky Way comes from this idea, from the Greek words galaxias kaiklos, meaning milky circle. The story blends the familiar act of nurturing with the vastness of the heavens, turning the everyday into something cosmic. Other cultures saw the glow differently. In China, the Milky Way was known as the Silver River, and it played a role in one of the most enduring love stories of Chinese folklore. It tells of a weaver girl and a cowherd, two lovers separated by the River of Stars. Once each year, on the 7th day of the 7th lunar month, a bridge of magpies forms across the Silver River, allowing them to meet. This story is celebrated in the Cixi festival, sometimes called the Chinese Valentine's Day. In this view, the Milky Way is not just a backdrop but an obstacle, a boundary between lovers, and at the same time a source of hope, because it promises reunion. In many parts of the world, people describe the Milky Way as a road. In South America, the Inca saw it as a celestial river, mirroring rivers on Earth. They believed it played a role in agricultural cycles, linking the patterns in the sky to the water that nourished their crops. To some Native American tribes, the band of light was a path travelled by spirits on their way to the afterlife. In parts of Africa, it was described as the backbone of night, a structural feature of the sky itself, holding everything together. The sense that the Milky Way was not just light but a path, a journey, or a support was common across cultures. These stories may sound different, but they share a pattern. People saw something vast and unexplainable, and they related it to things they knew: milk, rivers, roads, bridges, backbones, all familiar elements of daily life. By projecting them onto the sky, the unknown became understandable, even intimate. The galaxy overhead was not a distant collection of stars, but something connected to human experience. It was nourishment, movement, love, or structure. In that way, the stories brought the cosmos down to Earth. The ancient Egyptians also wove the Milky Way into their beliefs. They associated it with the goddess Nut, who stretched across the sky, her body forming the arch of heaven. The Milky Way was seen as a manifestation of her presence, a band of light across her form. To them, the sky was alive with divine figures, and the glowing arc was a visible reminder of the gods. Just as the Nile was the central river of their land, so too was the Milky Way a river of the heavens. The symmetry between earth and sky gave order to their worldview, linking natural cycles to celestial ones. In Finland, the Milky Way was called Linnunrata, which means the path of the birds. It was believed that migrating birds used the band as a guide, following it across the seasons. While we now know birds navigate partly by the stars, the idea that they literally followed the Milky Way gave the galaxy a practical role in explaining animal behaviour. The night sky wasn't distant in these traditions. It was directly tied to life on the ground, to the movement of seasons and creatures. In Australia, Aboriginal peoples had their own interpretations, rich and varied depending on region. Many saw the Milky Way not just as a collection of stars, but as both light and shadow. The dark lanes cutting through the band were seen as important figures in their stories. In one tradition, those dark patches formed the image of an emu stretching across the sky. The appearance of the emu in the sky at certain times of the year marked the season for collecting emu eggs. Here again, the Milky Way was not abstract. It was a tool for survival, integrated into the cycle of food and time. Among the Maya of Central America, the Milky Way was seen as the tree of life, a cosmic structure connecting the heavens, earth, and the underworld. Its branches stretched across the sky, linking realms and providing order to the cosmos. In this vision, the galaxy was not just a feature of the night, but a symbol of balance and connection. The Milky Way was the axis around which existence was organized. These interpretations highlight something important. The Milky Way is universal. Unlike individual constellations, which appear differently depending on where you live, the band of the galaxy crosses the whole sky. It may rise and set in different positions, but everyone sees it in some form. That universality meant that every culture had reason to explain it. And because they did so independently, we are left with a tapestry of myths, legends, and stories that echo across continents. They differ in detail, but resonate in theme. The Milky Way is a river, a road, a bridge, a backbone, a tree, a goddess, or a path of spirits. Always something fundamental, always something tied to human life. As astronomy developed, these stories gave way to scientific explanations, but the sense of wonder remains. In some ways, the myths preserved a truth, even if not a literal one. They recognized that the Milky Way is essential, that it is a structure on which we depend. Today we know it as the galaxy that houses our sun, earth, and everything we know. But the stories remind us that long before science, people sensed its importance. They didn't know about dark matter or star formation, but they knew the Milky Way mattered. Even now, the old names and myths linger. When we call it the Milky Way, we are still repeating the Greek image of spilled milk. When we speak of the Silver River, we are echoing Chinese folklore. When Australians talk of the emu in the sky, they are preserving traditions that are tens of thousands of years old. Science has added detail and measurement, but it hasn't erased the cultural meaning. The Milky Way is both an object of study and a source of stories. It is both a galaxy and a legend. It's worth imagining what it must have been like to live in a world where the Milky Way was a nightly presence, where the stars were countless and bright, and the galaxy stretched clearly from horizon to horizon. Without artificial light, the band was vivid, undeniable. Every child saw it. Every traveller relied on it. Every community built it into their sense of the world. Today, in many places, people can go their entire lives without seeing it clearly. They may grow up hearing about it, seeing photographs, but never experiencing the arc of light for themselves. Something that was once universal has become rare, and that rarity makes the ancient stories even more remarkable, because they were not written by scholars with telescopes, but by ordinary people who simply looked up. Those people had no way of knowing what we know now, yet their stories were not meaningless. They reflected an attempt to connect the human world with the cosmic. They gave the galaxy a role in guiding, nourishing, or protecting. They made sense of its presence by linking it to things that mattered in daily life. When you hear the story of Hera's milk, or the bridge of magpies, or the emu in the sky, you're hearing echoes of how deeply the Milky Way was woven into the human imagination. In that sense, the ancient stories of the Milky Way are not just curiosities from the past. They are part of our collective relationship with the night sky. They show how humans, everywhere, have always sought to explain what they saw, always tried to find meaning in the vastness above. Whether through myth or science, we are driven to understand. The difference lies in the tools we use, but the impulse is the same. And so, when we ask what the Milky Way is, we can answer in two ways. It is a galaxy, vast and ancient, measured and mapped by science. But it is also a river of stories, a band of imagination stretching across cultures and centuries. It has always been both. When people first began to wonder how many stars fill the Milky Way, they faced an impossible task. To the naked eye, the sky seems sprinkled with countless points of light, more than anyone could tally. In reality, on the darkest night, far from artificial lamps, the human eye can see only a few thousand stars. That number feels immense, but it is just the surface. The true population of the Milky Way is so much larger that it almost resists comprehension. Astronomers estimate that there are between 100 billion and 400 billion stars in our galaxy alone. Some estimates even stretch higher, depending on the method used. Trying to imagine numbers that large is like trying to hold the ocean in your hands. The attempt to count stars goes back to the earliest astronomers with telescopes. In the 17th century, Galileo turned his small instrument to the hazy band of the Milky Way. What looked like mist to the eye resolved into countless tiny stars. The glow was not fog, but the combined light of more suns than could be counted individually. Galileo did not try to put a number on them, but he understood the scale was far beyond human sight. Over the centuries, larger telescopes and better techniques have given us more information, yet even now the exact number is unknown. Counting stars is not as simple as pointing a telescope and tallying what appears. The galaxy is too large, too filled with dust and gas that obscure light, and too crowded in places for stars to be separated cleanly. Astronomers rely on indirect methods. They measure the amount of light coming from the galaxy and estimate how many stars it must represent. They analyze the mass of the Milky Way by observing how fast stars orbit around its center and compare that mass to the average size of stars. They also study nearby regions, count stars there, and extrapolate to larger scales. Each method comes with uncertainties, which is why the number is given as a range. But even with the uncertainty, one thing is clear. The Milky Way contains hundreds of billions of stars. Numbers like that are hard to make real. If you tried to count to 1 billion aloud, saying one number per second, it would take more than 30 years without stopping. Multiply that by a few hundred, and you begin to sense how vast the population of the Milky Way is. And remember, each star is not just a point of light. Each is a sun, a sphere of nuclear fusion producing energy. Many of those stars likely host planets, and some of those planets may have moons. The sheer abundance makes the night sky seem almost modest compared to what lies beyond the reach of our eyes. Not all stars are the same. Some are enormous, blazing with energy, burning through their fuel quickly and ending in spectacular explosions. Others are small and dim, glowing faintly for trillions of years, so stable that they outlast generations of larger stars. The Milky Way's population includes every type, from massive blue giants to tiny red dwarfs. By far the most common are the red dwarfs, stars smaller and cooler than our Sun. They make up perhaps 3/4 of all stars in the galaxy. Because they are faint, few are visible without telescopes, yet they dominate in number. The stars that stand out to our eyes, the bright ones that form constellations, are mostly larger, rarer types that shine strongly enough to pierce the distance. Our Sun is an ordinary star, a yellow dwarf, neither especially large nor especially small. It belongs to the middle class of stars. It is bright enough to support life on Earth, but common enough that there are billions like it scattered across the galaxy. For every star like the Sun, there are many more that are smaller and dimmer. If you were to travel through the Milky Way, most of the stars you passed would not be dazzling giants, but quiet, red embers glowing steadily. Beyond stars and planets, the Milky Way also contains exotic objects. White dwarfs, the remnants of stars that have burned through their fuel. Neutron stars, the collapsed cores of massive suns, so dense that a teaspoon of their matter would outweigh mountains. Black holes, both the supermassive one at the centre and smaller ones scattered throughout, formed from the collapse of massive stars. These objects are not as numerous as ordinary stars, but they are part of the population, hidden within the billions. Each adds to the complexity of the galaxy's story. When astronomers estimate the number of stars, they are also estimating the number of possible solar systems. In recent decades, with the discovery of exoplanets, planets orbiting stars beyond our Sun, we've learned that planets are common. Nearly every star studied closely enough has at least one. Many have several. Some have systems that resemble our own, with multiple planets orbiting in a dance of gravity. Others have worlds unlike anything in our imagination. Gas giants hugging close to their suns, planets larger than Jupiter orbiting in days instead of years, rocky planets so hot their surfaces may be oceans of lava, or frozen bodies drifting in the cold reaches of distant orbits. If even a fraction of the billions of stars in the Milky Way have planets, then the galaxy must contain trillions of worlds. This realization changes how we see the night sky. Those points of light are not only stars, but also potential homes for worlds. Somewhere among the billions there may be planets with oceans, continents, and skies of their own. The thought that our galaxy is filled with such possibilities adds another layer of wonder to the idea of counting stars. It is not just the number of suns that matters, but the number of systems, each one a stage where stories of matter, chemistry, and maybe even life might play out. In trying to count stars, astronomers also confront the limits of observation. Dust clouds block light in many directions, hiding stars from view. Some regions of the Milky Way are so crowded that individual stars blur together. Others are faint, their light spread thin over vast distances. Technology helps. Infrared telescopes can peer through dust. Radio observatories detect signals from gas clouds, revealing structures invisible in light. Surveys like those conducted by the Gaia spacecraft map the positions and motions of billions of stars, building a three-dimensional picture of the galaxy. These projects bring us closer to an accurate census, though the final number may never be known with certainty. Even if the exact count is elusive, the scale itself is undeniable. Hundreds of billions of stars in one galaxy, and our galaxy is only one among an estimated 2 trillion in the observable universe. If every galaxy holds a similar number, the total stars in the cosmos reach numbers that defy imagination. Yet we live in one, orbiting one star, in one arm of one galaxy. Counting stars reminds us not only of abundance but of perspective. It also reminds us of how far knowledge has come. For most of history, the number of stars was assumed to be large but finite, perhaps only as many as could be seen with the eye. The idea that there were hundreds of billions in the Milky Way alone would have seemed impossible. Each advance in technology expanded the number. Galileo's telescope multiplied the known stars. Later instruments expanded the field further. Modern space telescopes have multiplied it again. Each generation discovers that the sky is fuller than anyone had realized. The phrase, billions upon billions, has become almost cliché in discussions of stars, but it conveys something true. The Milky Way is not just a collection of lights, but a vast, structured population. Every star contributes to the glow of the band across the night. Every one is part of the fabric of the galaxy. To count them is not only to measure, but to acknowledge the richness of the system we live in. For anyone standing beneath the night sky, the effort to count stars may feel unnecessary. The sight itself tells the story. There are more than you can hold in your mind, more than you can point to one by one. You could spend an entire night naming them and still not make a dent. That experience of being overwhelmed by abundance is part of the wonder. It is the same feeling astronomers put into numbers when they say billions. Both the feeling and the figure point to the same truth. The Milky Way is immense, populated beyond easy reckoning, filled with suns of every type and age, scattered across 100,000 light years. As we move deeper into understanding the Milky Way, the sheer number of stars is a foundation. It shapes the gravity of the galaxy, the recycling of matter, the potential for planets, and the probability of life. The Milky Way is not a sparse collection. It is crowded, dynamic, and endlessly varied. And while the precise number may remain uncertain, the reality is that we're surrounded by abundance on a scale that stretches the imagination. When you look up at the night sky, you can only ever see the Milky Way from the inside. That limitation shapes everything about how we understand it. Imagine living in the middle of a forest. You see trees stretching around you in every direction. But from the ground, you cannot step back and take in the whole pattern of the woods. You might guess at its extent, perhaps even climb a hill to gain perspective, but the full shape remains hidden. In much the same way, living inside the Milky Way means we cannot step outside to take a photograph of its form. Every picture you have ever seen of our galaxy as a spiral with long arms, curling outward, is either an artist's rendering or a photograph of a similar galaxy elsewhere. What we know about the Milky Way shape comes from careful deduction, piecing together evidence gathered star by star, cluster by cluster, and gas cloud by gas cloud. The broad picture that emerges is that the Milky Way is a barred spiral galaxy. That means it has a flat disc-like structure, with stars arranged in a pattern of spiral arms radiating outward from a central bar-shaped core. The bar itself is made of stars, stretched across the middle of the galaxy. From the ends of that bar, arms unwind, forming a graceful pattern that circles the disk. Spiral galaxies are among the most beautiful structures in the universe, and the Milky Way is one of them. Though we see it only from within, our perspective limited to narrow lines of sight through the disk. Spiral arms are not solid objects. They are not fixed structures like the branches of a tree or the spokes of a wheel. Instead, they are patterns created by density waves. Imagine traffic on a highway. Cars flow along at different speeds, but sometimes they bunch up, creating a wave of congestion. The wave moves along the road, even though the individual cars pass through it. Spiral arms work the same way. Stars, gas, and dust orbit the center of the galaxy, and in certain regions they are compressed into higher density. These denser areas are the spiral arms. Stars are born there in large numbers, especially the bright, short-lived blue giants that make the arms stand out. Over time, those stars burn out, leaving behind fainter remnants. But by then, new stars have formed in the arm further along. The arms are not permanent in the sense of being made of the same stars forever. They are patterns, continuously refreshed as matter flows through them. From Earth's location, about 27,000 light-years from the galactic center, we see evidence of several arms. The most prominent are named the Perseus arm, the Scutum Centaurus arm, and the Sagittarius arm. Our solar system sits not in a major arm but in a smaller spur, sometimes called the Orion arm or Orion spur, nestled between larger structures. This location is something of a cosmic suburb, away from the most crowded regions but still within reach of the galaxy's main features. From here, the band of the Milky Way appears as a hazy stripe because we are looking edge-on through the disk. In the direction of Sagittarius, we peer toward the center, where the bulge and bar dominate. In the opposite direction, we look outward toward the thinner edges where fewer stars are visible. The arms themselves are vast. Each stretches across tens of thousands of light-years, containing billions of stars. Interwoven with them are clouds of gas and dust, the raw material for star formation. Nebulae like the Eagle Nebula, the Lagoon Nebula, and the Orion Nebula are all located within arms. These glowing regions mark the places where new generations of stars are taking shape. They are nurseries, lit by the intense radiation of young, massive stars that ionize the surrounding gas. The presence of so many bright nebulae and clusters makes the arms the most spectacular parts of the galaxy. If you were able to see the Milky Way from far away, its arms would not look like crisp, evenly spaced lines. They would appear somewhat patchy, with segments of brightness broken by darker regions. The overall spiral pattern would be clear, but the details would be messy. That patchiness reflects the dynamic nature of the arms. Stars are constantly forming, dying, and drifting, and gas clouds are shaped by supernova explosions, stellar winds, and gravity. The result is a structure that is both ordered and chaotic, both patterned and turbulent. At the center of the galaxy lies the bar. This elongated feature, about 27,000 light-years long, is composed of stars orbiting in elongated paths. Bars are common in spiral galaxies, though they were once thought to be unusual. Observations suggest that 2/3 of all spiral galaxies have bars. These structures may play a role in channeling gas toward the central regions, feeding star formation near the core, and perhaps fueling the activity of the central black hole. In the Milky Way, the bar connects directly to the spiral arms, linking the crowded bulge to the outer disk. The bulge itself is a spheroidal region of stars, thicker than the disk, with a mix of old and young populations. Stars there orbit in complex paths, influenced by the central mass of Sagittarius A, the supermassive black hole. From Earth, the bulge is visible in the direction of the constellation Sagittarius, where the Milky Way looks brightest. Dust clouds obscure much of it, but infrared and radio observations reveal a crowded, dynamic environment. The heart of the galaxy is not calm but bustling, with stars packed closely together and gas clouds moving under intense gravitational forces. Surrounding all of this is the halo, a diffuse, roughly spherical region that extends far beyond the visible disk. The halo contains old stars and globular clusters, some of the oldest structures in the galaxy. It also holds most of the dark matter, the invisible mass that outweighs all the visible stars combined. The halo does not shine like the disk or arms, but its gravitational influence shapes the motion of everything within the galaxy. Without it, the spiral pattern would not hold together. Understanding the shape of the Milky Way has been a slow process. In the 18th century, William Herschel attempted to map the galaxy by counting stars in different directions. His map suggested a flattened disk with the sun near the centre, but it was limited by dust that blocked his view. Later, in the early 20th century, Harlow Shapley used globular clusters to estimate the true centre, shifting our perspective and showing that the sun was not central, but located far out toward the edge. Radio astronomy in the mid-20th century added more detail, mapping the distribution of hydrogen gas and tracing the spiral arms. Modern surveys, including space-based observatories like Gaia, now provide detailed maps of billions of stars, refining our understanding further. Each step has revealed more complexity, more structure than previously thought. Despite all this progress, the exact shape of the Milky Way is still not fully known. The number of spiral arms, their exact paths, and the details of the bar remain topics of study. Dust continues to obscure large parts of the disk, making it difficult to see clearly. From our vantage point, we build models, but there is always room for revision. The Milky Way is not a simple picture in a textbook, but a living system, full of intricacies that reveal themselves slowly as technology improves. Thinking about the galaxy's shape also highlights our place within it. We are not at the centre, nor at the edge, but somewhere in between, in a modest spur of a spiral arm. This position offers advantages. It is relatively quiet compared to the core, where radiation and crowding could pose risks to life. It is also not so isolated that we are cut off from the richness of the galaxy. We orbit in a zone that is balanced, providing stability over billions of years. That stability has allowed life on Earth to develop and persist. In a way, the shape of the Milky Way has shaped us. When you imagine the arms stretching outward, filled with stars and nebulae, it is worth remembering that we see only hints of them from Earth. The Orion spur where we live gives us a local perspective, but the true sweep of the spiral is hidden. Photographs of other spiral galaxies, Andromeda, the whirlpool, the pinwheel, give us analogues, pictures of what we suspect our own looks like. They show us the beauty of spiral patterns, the elegance of arms unfurling across space. By comparing them to our measurements, we fill in the blanks of our own galaxy's image. In the end, the Milky Way shape is not just an abstract fact. It is the structure that holds us, the context in which every star we see at night is located. The arms are not decorations, but the framework of our home. To know their form is to begin to know the architecture of the galaxy itself. and though we may never step outside to see it directly, we can imagine it. A great barred spiral, arms curling outward, glowing with the light of billions of stars, and within one quiet spur, a small star with a handful of planets, one of which has listeners like you wondering about the shape of it all. When you think of an address, you might picture something ordinary, like a street name, a house number, a city and a country. These markers tell others where you live, placing you within a larger structure of maps and borders. But if you zoom out far enough, if you look past continents and oceans, past the planet itself, there is another kind of address to consider. It is not written on mail or carved into signs. It is the place of our solar system within the vastness of the Milky Way, our position in a spiral galaxy that stretches across 100,000 light years. To know our cosmic address is to know not only where we are, but also what kind of environment surrounds us. The Milky Way is shaped like a barred spiral, with arms winding outward from a central bar. These arms are not rigid structures, but regions of higher density, waves of matter where stars are born in greater numbers. Our Sun, and with it the Earth and everything familiar, does not reside in one of the great sweeping arms like Perseus or Scutum Centaurus. Instead, we are located in a smaller structure, sometimes called a spur, nestled between larger arms. This feature is known as the Orion Arm, or more specifically the Orion Spur. It is not the grand highway of the galaxy, but more like a side road, a quieter lane running alongside the main routes. From our position within the Orion Arm, we see the Milky Way as a glowing band across the sky. Looking towards Sagittarius, we peer inward toward the galactic centre, where the bulge and bar dominate, crowded with stars. Turning the other way, we look outward, toward the thinner edges, where the arms trail off into less dense regions. Our location gives us a balanced view, neither too close to the bright, crowded core nor too far into the sparse outskirts. This middle position shapes everything about our experience of the galaxy. The Orion Arm itself is about 3,500 light-years across and 10,000 light-years long. That may sound enormous, but compared to the major arms, it is modest. It is bounded by the Perseus Arm on one side and the Sagittarius Arm on the other. We sit roughly halfway between them, tucked into this spur like a small neighbourhood between larger cities. Despite its relative modesty, the Orion Arm is rich in features. It contains several well-known nebulae, including the Orion Nebula, which gives the arm its name. This bright nearby region of star formation is visible to the naked eye as a faint patch in the sword of the constellation Orion. Telescopes reveal it as a spectacular cloud of glowing gas and dust, lit by young stars just beginning their lives. The presence of such a nursery makes the Orion Arm significant, because it is not only home to mature stars like the Sun, but also a place of ongoing creation. Within the Orion Arm lies the solar system, orbiting the galactic centre at a distance of about 27,000 light-years. The Sun moves at roughly 828,000 km per hour, completing a full circuit of the galaxy in about 225 million years. During its lifetime, it has made only a handful of such orbits, each one carrying it through different regions of the disk. Right now, we're in a relatively calm area, far from the disruptive influence of the galactic centre. This stability may be one reason life on Earth has been able to flourish. The conditions here are gentle compared to the core, where stars crowd so tightly, and radiation is so intense that life as we know it would face enormous challenges. The Orion Arm also hosts familiar constellations. Orion, Perseus, Cygnus, and Cassiopeia are all shaped by stars in this region. When you trace those patterns in the night sky, you're sketching the outlines of our neighbourhood in the galaxy. They are local landmarks, in a sense, the way hills or rivers mark a terrestrial map. Beyond them, the stars thin into more distant structures, but these constellations give us a reference, a way to orient ourselves within the arm. Being in the Orion Arm also means we are surrounded by clusters and associations of stars. Open clusters like the Pleiades and the Hyades, both in the constellation Taurus, are relatively nearby. They are groups of stars born together from the same cloud, still loosely bound by gravity. These clusters remind us that stars often form in groups, and though most eventually drift apart, their shared origin leaves a trace. Our Sun may have once belonged to a cluster, though its siblings have since scattered across the galaxy. Somewhere out there, other stars share our origin story, though identifying them is difficult after billions of years of motion. If you look beyond the Orion Nebula, other striking features of the arm come into view. The Eagle Nebula, famous for the Pillars of Creation photograph taken by the Hubble Space Telescope, lies within our spur. The Carina Nebula, another immense star-forming region, is also part of our neighbourhood, though visible mostly from the southern hemisphere. These regions are reminders that the Orion Arm is not static. It is alive with activity, producing new generations of stars that will light the galaxy for millions of years to come. Our cosmic address is not only a location but also a trajectory. The solar system is moving, carried along with the arm as it orbits the galactic centre. The Orion Arm itself is not fixed but slowly shifts as density waves propagate through the disk. Over millions of years, our position relative to other arms may change. The stars we see as neighbours today will not always be close. Already, the constellations are slowly shifting, their shapes distorting over millennia as stars drift along their paths. The Orion Arm is a temporary arrangement, stable on human timescales, but fluid on cosmic ones. Understanding our place in the Orion Arm also depends on recognising what surrounds us. To one side, the Perseus Arm stretches outward, one of the galaxy's main spirals. To the other side lies the Sagittarius Arm, closer to the galactic centre. Between these lies the Bar and Bulge, where stars crowd together in greater density. Compared to those regions, the Orion Spur is quieter, less populated, but still filled with features of interest. It is, in a sense, the right balance between bustle and calm. Astronomers only pieced together the existence of the Orion Arm in the 20th century. By mapping the positions of star-forming regions, they realised that the Sun was not located in a major arm but in this smaller spur. For a long time, it was assumed the Sun must be in one of the grand structures, but careful measurements showed otherwise. This discovery added nuance to our picture of the galaxy, reminding us that not every part is the same. There are great arms and smaller bridges, bars and bulges, each contributing to the whole. Our home happens to be in one of the modest features, not in the most spectacular, but in one that offers stability. This stability has profound implications. In the denser arms, supernovae are more common. Massive stars live and die quickly, and radiation levels can be higher. By residing in a smaller spur, at a comfortable distance from the core, our solar system may have avoided many of the disruptions that could have threatened the development of life. That does not mean we are immune to cosmic events. Supernovae, gamma-ray bursts and passing stars all remain possibilities, but our location reduces the risks compared to more crowded neighbourhoods. It is tempting to think of the Orion Arm as unremarkable, a small spur in a galaxy of grander features, yet it is remarkable to us because it is home. Every human story, every life, every civilization has unfolded here. The light we see at night, the constellations we trace, the nebulae captured in photographs. They are all part of this region. When we speak of a cosmic address, it is not abstract. It is as real as any street or city, the context that shapes our environment. And while we may not often think about it, knowing our address matters. Just as a sailor needs to know their position on a map, so too do astronomers need to know our place in the galaxy. It allows us to understand the view we have, to interpret what we see in the sky, and to build models of the Milky Way's structure. Without that knowledge, the band of light overhead would remain only a mystery. With it, we recognize it as the inside view of a spiral, seen from within one of its arms. The Orion Arm, modest as it is, has given us everything. It holds the Sun, which has burned steadily for 4.6 billion years, providing the energy that drives life. It holds the Earth, with its oceans and continents, atmosphere and ecosystems. It holds the neighbouring stars we see at night, the clusters and nebulae that decorate our skies. It holds the raw material for future stars and planets, clouds of gas that will one day collapse into new systems. It is our neighbourhood, familiar yet vast, close yet expansive enough to remind us of scale. To know our cosmic address is to take a step toward belonging. We are not adrift in the galaxy without context. We are located in a specific spur, orbiting at a specific distance, moving along a specific path. That knowledge anchors us, the way a map anchors a traveller. And as we continue to learn more about the Milky Way, our picture of this address becomes clearer, more detailed, more real. When you imagine the Milky Way, it is easy to picture it as a great still photograph, a glowing spiral frozen in space, but nothing about it is still. Every part of the galaxy is in motion, from the smallest dust grains drifting in clouds to the largest star clusters orbiting the core. The Milky Way is not a static object, but a dynamic system, alive with movement, shaped and reshaped by the invisible hand of gravity. If you could speed up time, watching millions of years pass in minutes, the galaxy would look like a great whirlpool of light, arms curling and twisting, stars orbiting in great circles, clouds colliding and fragmenting, clusters scattering, and whole regions bending under the influence of unseen mass. The calm band of stars we see at night is, in truth, the face of a dance that has been unfolding for billions of years. Gravity is the choreographer of this dance. It is the weakest of the fundamental forces, yet across large scales, it dominates everything. Every star is pulled toward every other, but the combined pull of billions organizes into a structure. At the heart of the Milky Way is a supermassive black hole, Sagittarius A's, with a mass of around 4 million suns. Its gravity holds sway over the stars closest to the centre, which whip around it in dizzying orbits. But beyond that central region, the pull of the entire galaxy's mass takes over, keeping stars bound in their paths around the disk. Without gravity, the Milky Way would disperse, its stars scattering into space. With it, the stars remain together, moving in orderly but complex patterns. The Sun, along with Earth, orbits the centre at a distance of about 27,000 light-years. It moves at an average speed of about 828,000 kilometers per hour. At that pace, it takes roughly 225 million years to make one full orbit. That means in the entire history of our species, humanity has not even completed a fraction of a galactic year. Since the dinosaurs roamed Earth, the solar system has circled the galaxy only once. By the time the Sun reaches the end of its life, billions of years from now, it will have made perhaps 20 revolutions. To us, the motion is imperceptible. The stars appear fixed from one night to the next. Yet over millennia, constellations shift, stars drift, and the slow choreography reveals itself. Not all stars move at the same pace. Those closer to the galactic centre orbit faster, pulled more strongly by the greater concentration of mass. Those farther out orbit more slowly. But here is where a mystery arises. If you calculate the orbital speeds based only on the visible stars and gas, the outer regions of the galaxy should move much more slowly than they actually do. Observations show that stars far from the centre orbit at nearly the same speed as those closer in. This discrepancy was one of the first strong pieces of evidence for dark matter, the invisible substance that makes up most of the galaxy's mass. Dark matter does not emit light, but its gravity shapes the dance of stars, holding the outer disk in place and flattening the rotation curve. Without it, the Milky Way's outer stars would drift away, unbound. With it, the galaxy's dance remains coherent. The stars themselves do not move in perfect circles. Their orbits are often elliptical, sometimes tilted relative to the disk, sometimes perturbed by encounters with other stars or clusters. Groups of stars move together in streams, the remnants of smaller galaxies that were absorbed into the Milky Way. These stellar streams arc across the sky, evidence of past mergers. They remind us that the Milky Way has not always been as it is now. It has grown by accreting smaller galaxies, their stars pulled into new paths by gravity. The galaxy's dance is not only orderly but also turbulent, shaped by collisions and interactions that leave long-lasting marks. Inside the spiral arms, the dance takes on another layer of complexity. Gas clouds orbit along with stars, but as they pass through regions of higher density, they are compressed. That compression triggers star formation, leading to clusters of bright, short-lived stars. These massive stars burn hot and fast, dying in supernova that send shockwaves through surrounding clouds. Those shockwaves compress new regions, triggering more star formation. The result is a cycle, a rhythm of birth and death, creation and destruction, all orchestrated by gravity. The spiral arms glow with this activity, the dance of stars constantly refreshed. Globular clusters, those dense spherical groups of stars in the galactic halo, add another element to the dance. They orbit the Milky Way on long, looping paths, some plunging through the disk, others circling far out in the halo. These clusters are ancient, relics from the galaxy's youth, their stars bound tightly by mutual gravity. As they move, they interact with the disk, their gravity tugging on stars and leaving subtle imprints on the motions of others. They are like dancers on the edge of the stage, moving to the same rhythm but in wider, slower arcs. The central bulge and bar also have their own motions. Stars there orbit in complex patterns, influenced by the elongated structure of the bar. Some follow orbits aligned with the bar, others loop around it, creating a mix of paths that give the bulge its shape. The bar itself may rotate, dragging stars and gas along, funneling material toward the center. This flow of gas can fuel star formation near the core and occasionally feed Sagittarius Aund, causing it to flare with bursts of energy. Even at the heart of the galaxy, where orbits are shortest and speeds are greatest, the dance remains a balance between order and chaos. If you could watch the Milky Way stars speeded up, you would see patterns emerge. Spiral arms winding and unwinding, clusters forming and dispersing, streams stretching across the halo, stars plunging through the disk. You would see the sun and its neighbours circling steadily, carrying their planets along. You would see the outer halo stars orbiting more slowly but still bound by the unseen mass of dark matter. You would see the galaxy as a living system, never still, never fixed, always moving. On smaller scales, the dance is just as intricate. Binary stars orbit each other, sometimes close enough to exchange mass. Triple systems twist in complex gravitational interactions. Planets orbit stars, moons orbit planets, and rings orbit within those systems. Each motion is part of the larger whole, a nested hierarchy of orbits, all governed by the same force. From moons circling gas giants to stars circling the galactic center, gravity dictates the steps. Our place in this dance is humble. The solar system is a participant, one among billions, moving in its orbit without pause. We do not feel the motion, but it is constant. At this moment, as you listen, Earth is being carried through space at hundreds of thousands of kilometers per hour, tracing its long arc around the galaxy. The dance is invisible to us day by day, yet it defines our place in the cosmos. The Milky Way's dance also points to its future. In about 4 billion years, it will merge with the Andromeda galaxy. Even now, the two are moving toward each other at roughly 110 kilometers per second. When they collide, their stars will not crash head-on. The distances between stars are too vast, but their orbits will be altered. The two galaxies will pass through each other, drawn back together by gravity, and over billions of years they will merge into a new, larger galaxy, sometimes called Milkomeda. The dance of stars will be reshaped, new streams will form, new structures will emerge. The galaxy's choreography will continue, but with new partners on the stage. Thinking about the Milky Way as a dance helps make sense of its complexity. It is not static, not frozen, but alive with motion on every scale. Gravity is the rhythm, steady and universal, pulling stars into orbits, shaping arms, guiding clusters, binding the whole together. The stars are the dancers, each tracing its path, each part of the pattern. Some move swiftly, others slowly. Some follow simple arcs, others weave in complicated loops. Together they form the galaxy we see, the great spiral glowing in the night. And here we are inside it, participants without noticing, carried along by the same rhythm that governs all. Every time you look up and see the stars, you're seeing the mid-step in a dance that began long before humans walked the earth and will continue long after. It is a reminder that motion is everywhere, that stillness is only an illusion, and that the galaxy itself is a performance unfolding on scales of time and space beyond our everyday comprehension. At the centre of the Milky Way lies a secret that took us a long time to uncover. For most of human history, the core of the galaxy was simply the brightest part of the band in the night sky, glowing through the constellations of Sagittarius and Scorpius. To the naked eye, it looked crowded, dense with light, impossible to separate into individual points. With telescopes, more detail appeared: clusters, nebulae, and intricate dark lanes of dust slicing across the glow. Yet even with those tools, the true nature of the galaxy's centre remained hidden. Something was there, unseen but powerful, shaping the motion of stars, holding the structure together. That something is Sagittarius A, a supermassive black hole 4 million times the mass of the Sun, the hidden heart of our galaxy. The idea of a black hole was once purely theoretical, a strange solution to Einstein's equations of general relativity. At first it seemed too extreme to be real, an object so dense that not even light could escape its gravity. But over time, evidence accumulated that such things must exist. In the Milky Way, the strongest evidence comes from the orbits of stars near the galactic centre. Starting in the late 20th century, astronomers began tracking these stars with precise instruments. Over years and then decades, they watched as the stars traced tight, rapid loops around an invisible point. The speeds involved were enormous. Some stars whipped around at thousands of kilometers per second, completing orbits in just a few years. The only possible explanation for their motion was an object with millions of solar masses packed into a space no larger than our solar system. That object was Sagittarius A. Though invisible directly, Sagittarius A makes itself known through its effects. Occasionally gas clouds or stray stars venture too close, and their matter is torn apart by tidal forces. Some of the gas falls inward, spiralling around the black hole in an accretion disk. As it does, it heats to extreme temperatures, emitting radiation detectable across the electromagnetic spectrum. At times, Sagittarius A flares in X-rays and infrared light, brief flashes as matter plunges toward the event horizon. These outbursts are like a heartbeat, irregular, but telling us that the hidden heart is active. Despite its enormous mass, Sagittarius A is relatively quiet compared to the supermassive black holes in active galaxies. In some galaxies, black holes consume matter at a furious rate, producing jets of energy that shine brighter than all the stars around them combined. Our galaxy's heart is more subdued. It accretes matter slowly, flaring occasionally but not blazing continuously. This quietness may be a blessing. A more active black hole at the centre could flood the inner galaxy with radiation, making conditions less hospitable for life. As it is, Sagittarius A sits at the core, massive but mostly calm, a sleeping giant with rare moments of activity. The environment around the black hole, however, is anything but calm. The central region of the Milky Way, sometimes called the galactic nucleus, is crowded with stars. They are packed far more densely than in our neighbourhood of the Orion Spur. Some of these stars orbit in tight clusters, their paths bent sharply by the gravity of Sagittarius A. Others move in more chaotic patterns, jostled by encounters with neighbours. The density is so high that collisions between stars are more likely here than anywhere else in the galaxy. Gas clouds swirl through, compressed by gravity and radiation, sometimes collapsing into new stars, sometimes torn apart. The whole region is dynamic, a whirl of motion around the unseen anchor. Astronomers have learned to peer into this hidden heart using wavelengths of light that pass through the dust. Visible light is blocked by thick clouds in the disk, which is why the core is obscured to the eye, but infrared light slips through, as do radio waves and X-rays. By building instruments sensitive to these ranges, scientists have revealed structures that were once invisible. Radio telescopes have mapped Sagittarius A with extraordinary precision, while infrared telescopes have tracked the dance of stars around it. X-ray observatories have caught its flares, brief outbursts when matter is consumed. Piece by piece, the picture emerges of a core dominated by a black hole, surrounded by a complex environment of stars and gas. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A. It was not a crisp photograph, but a glowing ring surrounding a dark centre, created by combining radio signals from telescopes around the world. The image confirmed predictions of general relativity, showing light bent around the black hole's shadow. It was a profound moment, a glimpse of the hidden heart that had long been inferred but never directly seen. Though blurry, the image carried enormous weight. It was the face of the Milky Way's core, proof that the theories were right, that the dark centre we had imagined was real. The existence of Sagittarius A also tells us about the history of the Milky Way. Supermassive black holes are thought to form in the early stages of galaxy formation, growing as galaxies merge and matter falls inward. The fact that our galaxy has such a black hole suggests it went through similar processes. Over billions of years, Sagittarius A has grown to its current size, though compared to some black holes in other galaxies it is modest. Some cores contain black holes with billions of solar masses. Ours, at 4 million, is relatively small, though still vast by any human measure. The relationship between Sagittarius A and the galaxy is complex. It anchors the centre, shaping the orbits of stars in the bulge. It influences the flow of gas, sometimes drawing it inward, sometimes stirring it into turbulence. Yet it is not the sole controller of the Milky Way. The galaxy's mass is spread across stars, gas and dark matter, and their combined gravity dominates at larger distances. The black hole rules its immediate neighbourhood, but the galaxy as a whole is held together by far more than just its heart. Still, there is something profound about knowing that at the centre of everything we see in the night sky, there lies a point of no return, a place where gravity is so strong that time and space themselves are bent beyond recognition. From our quiet spur we are carried around this hidden heart, orbit after orbit, for billions of years. We do not feel its pull directly, but it defines the structure we live in. It is the silent centre, unseen by most, yet essential to the galaxy's existence. The thought of a black hole often brings images of destruction, of matter torn apart, of light swallowed. Those images are not wrong, but they are only part of the story. Black holes are also creators of structure. By their gravity, they shape the motions of stars, stabilize galactic centers, and influence the flow of matter. Without them, galaxies might not form as we know them. Sagittarius A is not just a destroyer, it is part of the balance, a necessary element of the galaxy's design. In reflecting on the hidden heart, there is also something humbling. We live our lives far from the centre, our concerns focused on Earth and its immediate sky. Yet orbit after orbit, we circle a core we cannot see, a black hole that quietly governs our galactic neighbourhood. It is a reminder of how much lies beyond direct experience, how much is hidden but still real. The stars overhead may seem serene, but deep in the heart of the Milky Way, gravity bends light itself, and the dance of stars whirls around an unseen anchor. As we think about the galaxy we call home, it is worth remembering that at its core is Sagittarius A, the black hole at the centre of everything. Not visible to the eye, not obvious in the night sky, but present, shaping and enduring. It is the hidden heart of the Milky Way, and through it we are bound to the structure of the galaxy, part of a story far larger than our own. Between the stars of the Milky Way there is not empty space. It might look that way when you glance up at the night sky, the pinpoints of starlight scattered across a black backdrop. But the darkness is misleading. The regions between stars are not voids. They are filled with gas, dust and radiation, a complex mixture that astronomers call the interstellar medium. Though it is extremely thin compared to the air you breathe, so thin that a cubic centimetre may contain only a few atoms, it is spread across such immense volumes that together it makes up a significant part of the galaxy's mass. The interstellar medium is the material out of which stars and planets are born, the raw ingredients recycled endlessly in a galactic cycle of creation and destruction. To imagine it, you have to set aside the idea of space as emptiness. Instead, picture an ocean, not made of water but of tenuous gas and fine dust grains, stretching between stars. This ocean is not uniform. Some regions are diffuse, filled with hydrogen atoms drifting widely apart. Others are dense, where clouds gather thick enough to block starlight. Within those clouds, under the pull of gravity, new stars form. In this way, the interstellar medium is not only the backdrop to the galaxy, but its engine, the source of every new generation of suns. The main component of the interstellar medium is hydrogen, the simplest and most abundant element in the universe. In its ionized form, where electrons are stripped away, it glows faintly in regions near hot stars. In its neutral form, with atoms intact, it fills the spaces between. And in its molecular form, where atoms pair up as H2, it collects into clouds dense enough to collapse into stars. Alongside hydrogen are helium and traces of heavier elements: carbon, oxygen, nitrogen, silicon, iron. The products of past stars that exploded and returned their contents to space. Every atom heavier than helium was forged in a star. That means the dust and gas drifting between stars are not just leftovers, but enriched matter, carrying the building blocks of future planets and life. Dust in the interstellar medium is not like dust on a bookshelf. It is made of tiny grains, often just fractions of a micron across, composed of silicates, carbon compounds, and ices. These grains absorb and scatter light, which is why some regions of the Milky Way look dark, crossed by lanes of shadow. To the eye, they appear as voids, places where stars are missing. But in reality, they are dense clouds rich with material. Dust also plays a role in chemistry, providing surfaces on which molecules can form. In the cold depths of molecular clouds, dust grains allow hydrogen atoms to bond into molecules, and more complex compounds can take shape. These processes are slow, taking millions of years, but across the galaxy, they add up to a chemical richness that seeds new systems. The interstellar medium is shaped constantly by energy from stars. Hot, massive stars emit intense ultraviolet radiation, which ionizes the gas around them, creating glowing regions known as H2 regions. These shine brightly in red and pink as hydrogen atoms recombine and release photons. The Orion Nebula is a nearby example, a glowing pocket of the interstellar medium lit by a cluster of young hot stars. Elsewhere, supernova explosions blast material outward, carving bubbles and shock waves in the medium. These shock waves compress nearby gas, triggering new star formation. The result is a cycle. Stars form from clouds, live their lives, release energy and matter, and stir the medium, which then produces new stars. The interstellar medium is never still. It is dynamic, a restless fabric of the galaxy. One of the most striking aspects of the interstellar medium is its scale. Molecular clouds can stretch across dozens or hundreds of light years. The famous Eagle Nebula, with its towering pillars of creation, is part of such a region. Inside those towering columns, dense knots of gas and dust are collapsing under gravity, forming new stars. Each knot may eventually light up as a sun with planets. To us, the pillars appear frozen in photographs, but in reality they are evolving, slowly eroding under radiation while also producing stars. On larger scales, whole complexes of clouds span thousands of light years, vast reservoirs of matter waiting to condense into new generations of stars. Despite its tenuous nature, the interstellar medium influences how we see the galaxy. Dust absorbs blue light more than red, reddening the starlight that reaches us. This effect, called interstellar extinction, dims distant stars and makes them appear redder than they truly are. Without accounting for it, our picture of the galaxy would be distorted. Astronomers measure how much light is absorbed and use that information to correct their maps. In doing so, they reveal the true brightness and colours of stars, and they uncover the structure hidden by dust. The interstellar medium also carries magnetic fields, threading through gas and dust. These fields are invisible but detectable through the way they align dust grains and influence the polarization of starlight. They play a subtle but important role in shaping clouds and regulating star formation. Without magnetic fields, clouds might collapse too quickly. With them, the process is slowed, balanced, and more complex. The galaxy's hidden magnetism is part of the unseen architecture of the medium, a quiet influence shaping its behavior. Cosmic rays, high-energy particles accelerated by supernovae and other energetic events, also move through the interstellar medium. They ionize atoms, trigger chemical reactions, and contribute to heating the gas. Though invisible to our eyes, they are a constant presence, reminders that the space between stars is not serene but active. Our solar system itself moves through the interstellar medium. At this moment, we are travelling through a region called the local interstellar cloud, a relatively thin patch of gas and dust. The heliosphere, the bubble formed by the solar wind, shields us from much of the medium, but traces still filter in. Tiny grains of interstellar dust drift into the solar system detected by spacecraft. They are travellers from the larger galaxy, carrying with them information about the environment beyond our planetary neighbourhood. In this sense, the interstellar medium is not distant, but immediate. It surrounds us, and we are moving through it continuously. Understanding the interstellar medium has been a gradual process. In the 19th century, astronomers noticed that some stars appeared dimmer and redder than expected, leading to the discovery of interstellar extinction. In the 20th century, radio astronomy revealed the distribution of neutral hydrogen across the galaxy, mapping its structure in unprecedented detail. Observations in infrared and submillimeter wavelengths have traced cold molecular clouds, showing where stars are being born. Today, space telescopes and ground-based observatories continue to refine this picture, revealing complexity upon complexity. The interstellar medium is not uniform, not static, but a patchwork of phases: hot, warm, cold, ionized, neutral, molecular, all interacting, all contributing to the life cycle of the galaxy. In many ways, the interstellar medium is the connective tissue of the Milky Way. It links stars to one another, provides the material for new generations, and carries the imprints of past events. When you see a dark lane cutting across the band of the Milky Way, you're seeing one of its features, a molecular cloud blocking starlight. When you see a glowing nebula, you're seeing it illuminated by newborn stars. The beauty of the night sky is shaped as much by the medium as by the stars themselves. Between the stars there are clouds, thin, diffuse and nearly invisible, yet essential. They are the cradles of creation, the archives of past generations, the stage on which the galaxy's ongoing story plays out. Without them, the Milky Way would be static, frozen, after its first burst of star formation. With them, it is alive, renewing itself across billions of years, recycling matter into ever new forms. When you look up at the night sky, the stars seem eternal. They shine steadily, appearing unchanged from one night to the next, and it is easy to imagine that they have always been there, fixed in place. But stars are not permanent. They are born, they live, and they eventually die. The glowing points you see overhead are part of a larger cycle, a process that has been going on since the galaxy's earliest days. At the centre of that process are the birthplaces of stars, nebulae, vast clouds of gas and dust that serve as stellar nurseries. The word nebula comes from the Latin for cloud, or mist, and for centuries that is what astronomers thought they were seeing. Faint, fuzzy patches of light in the sky, neither star nor planet, but something diffuse. With telescopes, the details became clearer, but even today the term refers broadly to many different kinds of clouds. Some glow with the light of nearby stars. Others are dark, silhouetted against the brighter background of the Milky Way. Still others reflect light, shining with a blue tint. What unites them is that they are places where the interstellar medium gathers thick enough to be visible, and where gravity can take hold to form new suns. Star formation begins in the coldest, densest regions of molecular clouds. These clouds are often hundreds of light years across, filled mostly with molecular hydrogen and laced with dust grains. Though the density is low by earthly standards, it is enough that over time regions within the cloud begin to clump. Small variations in density grow under the pull of gravity. Once a region gathers enough mass, it collapses inward. As the material falls, it heats, and at the centre a protostar begins to form. Nebulae are therefore more than just pretty pictures. They are the cradles of stars, where the raw gas and dust of the interstellar medium are transformed into the furnaces that light the galaxy. Every star you see was once hidden inside such a cloud. Our Sun too was born in a nebula about 4.6 billion years ago, surrounded by siblings that have long since scattered across the Milky Way. One of the most famous star-forming regions is the Orion Nebula, located about 350 light-years away in the constellation Orion. Visible to the naked eye as a faint smudge in Orion's sword, it reveals through telescopes a brilliant cloud of glowing gas, illuminated by a cluster of young, massive stars at its centre. These stars emit intense ultraviolet radiation that excites the surrounding hydrogen, causing it to glow in vivid reds and pinks. The Orion Nebula is a laboratory for astronomers, a place where the process of star birth can be studied in detail. Within it, dozens of protostars and protoplanetary disks have been observed, each one a system in the making. Another striking example is the Eagle Nebula, about 6,500 light-years away. Within it are towering columns of gas and dust, known as the Pillars of Creation. These structures, photographed in detail by the Hubble Space Telescope, have become iconic images of star formation. Inside the pillars, dense knots of material are collapsing into new stars. Radiation and stellar winds from nearby massive stars sculpt the columns, eroding them while also triggering more collapse. The scene is both destructive and creative, a vivid demonstration of how energy from one generation of stars shapes the birth of the next. In the Carina Nebula, located in the southern sky about 7,500 light-years away, the story is similar but on an even larger scale. This immense region spans hundreds of light-years and contains some of the most massive stars known, including Eta Carinae, a star so large and unstable that it is expected to explode as a supernova in the relatively near future. The radiation from these giants carves the surrounding clouds into intricate shapes, while within the shadows new stars quietly form. Carina is a reminder that nebulae are not static images but dynamic places, where matter flows, collapses, and reshapes itself constantly. Not all nebulae glow. Some are dark nebulae, visible not by the light they emit but by the light they block. The Horsehead Nebula, in Orion is one of the most recognizable, a dark silhouette shaped like the head of a horse standing out against the glowing background of nearby gas. Within it, dense regions are forming stars hidden from view. These dark nebulae are often the richest nurseries, their interiors shielded from radiation, allowing matter to cool and collapse. Reflection. Nebulae add another variety. These do not glow on their own, but reflect the light of nearby stars. The Pleiades star cluster, for instance, is surrounded by faint blue haze, light from hot, young stars scattered by dust grains. The effect is delicate, but it shows how dust not only blocks light but also reflects it, turning clusters into luminous jewels wrapped in mist. Planetary nebulae, though different in origin, also contribute to the galactic cycle. These are not birthplaces of stars, but the shells of gas ejected by dying stars. When a star like the Sun exhausts its fuel, it sheds its outer layers, which expand into space and glow under the ultraviolet light of the remaining core. These shells enrich the interstellar medium with heavy elements, which later become part of new clouds and new stars. Though not nurseries themselves, planetary nebulae are part of the cycle that makes nebulae fertile. Supernova remnants are another source of material. When massive stars end their lives in explosions, they blast their contents into the surrounding medium, creating nebulae like the Crab Nebula. These remnants are rich in heavy elements, forged in the star's core and in the explosion itself. They seed the galaxy with the ingredients for planets and life. The material they scatter becomes part of future star-forming clouds. The process of starbirth inside nebula is slow compared to human timescales. It can take millions of years for a region of a cloud to collapse into a star. Within that time, the balance between gravity pulling inward and pressure pushing outward shifts gradually. Protostars pass through stages, from faint infrared sources hidden in dust to bright, visible stars igniting nuclear fusion in their cores. Along the way, disks of material form around them, the seeds of planetary systems. Observations of protoplanetary disks in regions like the Orion Nebula show dark silhouettes against the glowing background, each one a potential solar system in formation. These disks are where dust grains stick together, grow into pebbles, then planetesimals, and eventually into planets. The same process once happened in the nebula that birthed our Sun, leaving behind the solar system we inhabit today. What makes nebulae so compelling is not only their role in star formation, but also their beauty. Photographs taken in visible, infrared, and ultraviolet light reveal colours and shapes that are both scientifically rich and visually striking. Reds from glowing hydrogen, blues from reflected starlight, greens from oxygen emission. These hues are not always visible to the eye, but are captured by long exposures and filters. The resulting images show the Milky Way's nurseries as vibrant landscapes, with mountains of gas, valleys of shadow, and rivers of dust. They remind us that creation in the universe is both physical and aesthetic, a process that produces beauty as a byproduct of physics. Nebulae are scattered throughout the Orion Arm, the region of the Milky Way where we live. That means they are part of our local neighbourhood in the galaxy. When you look at Orion rising in winter skies, or when you trace the band of the Milky Way through summer, you're looking toward regions where stars are forming right now. Some of the light reaching you left those nurseries long before humans existed. By the time it arrived, new stars may already have emerged from their cradles, their nebulae dispersed by winds and radiation. Star formation is a process we witness at a distance, frozen in time, but it is ongoing, continuous, and universal. Every star has its origin in such a nursery. The Sun's nebula has long since vanished, dispersed into the galaxy, but its memory lives in the planets it left behind and in the heavy elements of our world. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in stars and released into the interstellar medium, only to be gathered again into a new star-forming cloud. Nebulae are therefore not just distant curiosities, they are directly connected to us, part of the chain of creation that leads to life. When you think of nebulae, think of them not as isolated patches but as the wombs of the galaxy, places where matter gathers, collapses and begins anew. They are nurseries, busy with the quiet labour of forming stars, shaping planets, and setting the stage for everything that follows. Without them, the galaxy would be a graveyard of old stars with no renewal. With them, it is alive, continually refreshed, continually creating. Every star in the night sky has a story, though it is not one that unfolds on human timescales. The life of a star spans millions, sometimes billions or even trillions of years. Compared to that, our lives are brief flickers. Yet the stars, as eternal as they may seem to us, are not fixed or unchanging. They are born, they evolve, and they die. Their entire existence is written into the physics of gravity, nuclear fusion, and the balance of forces. By studying the stars of the Milky Way, astronomers have pieced together a narrative that applies universally. It is the life cycle of a star, a process repeated billions of times across the galaxy, each variation adding richness to the whole. The story begins, as we have already seen, in the cold depths of nebulae. A star is born when a knot of gas and dust in a molecular cloud collapses under its own gravity. As the material falls inward, it heats, forming a protostar. At first, the object is shrouded in dust, visible only in infrared. Over time, as it gathers more mass and pressure builds in its core, temperatures rise until nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, releasing energy. At that moment, the protostar becomes a true star. It shines not because it reflects light from others, but because it generates its own. Most stars spend the majority of their lives in what is called the main sequence, a long period of stability where hydrogen fusion in the core balances the inward pull of gravity. The energy produced pushes outward, counteracting the collapse. The result is equilibrium, a steady glow that can last billions of years. The exact length of this phase depends on mass. Small stars called red dwarfs burn their fuel slowly, sipping rather than consuming. They can shine for trillions of years, far longer than the current age of the universe. Larger stars, in contrast, burn furiously, fusing hydrogen at an accelerated rate. They may last only a few million years before exhausting their supply. The Sun, with a mass in the middle range, will spend about 10 billion years on the main sequence. It is currently about halfway through, a stable star in its long middle age. But stars do not remain in balance forever. When hydrogen in the core runs low, the equilibrium breaks. Gravity begins to win, compressing the core. The temperature rises, and in many stars, helium fusion begins, creating carbon and oxygen. The outer layers expand, and the star swells into a giant. For a star like the Sun, this phase will come in about 5 billion years. It will grow into a red giant, its radius expanding to engulf Mercury, Venus, and possibly Earth. Its outer layers will thin and drift outward, while the core shrinks into a dense remnant. For stars more massive than the Sun, the story is more dramatic. Their cores reach temperatures high enough to fuse heavier and heavier elements. Carbon into neon, neon into oxygen, oxygen into silicon, and silicon into iron. Each step releases energy, sustaining the star a little longer. But fusion of iron does not yield energy. When the core is mostly iron, the star can no longer support itself. The core collapses in a fraction of a second, and the outer layers rebound in a violent explosion, a supernova. These events are among the most energetic in the universe, briefly outshining entire galaxies. They scatter heavy elements into the interstellar medium, seeding the galaxy with the materials needed for planets and life. The remnants of stars depend on their mass. Low to medium mass stars like the Sun leave behind white dwarfs, small dense cores about the size of Earth, but with half the Sun's mass. These white dwarfs slowly cool over billions of years, fading into darkness. More massive stars collapse into neutron stars, objects so dense that a teaspoon of their matter would outweigh mountains. If the mass is even greater, the collapse continues into a black hole, a region where gravity is so strong that not even light can escape. These stellar remnants populate the Milky Way, unseen unless they interact with companions, yet numerous. They are the relics of past generations, markers of stars that once shone and died. The Milky Way is full of evidence of this cycle. Supernova remnants like the Crab Nebula show us the aftermath of explosions. White dwarfs are scattered throughout our neighbourhood, faint embers of stars long gone. Neutron stars reveal themselves as pulsars, rotating rapidly and emitting beams of radiation that sweep past Earth like cosmic lighthouses. Black holes reveal their presence when they pull matter from nearby stars, heating it until it glows in X-rays. These objects are reminders that stars are not eternal. They live, they change, and they leave behind traces that tell their story. The life and death of stars also explain the chemical makeup of the galaxy. The early universe contained mostly hydrogen and helium, with only trace amounts of heavier elements. Every atom of carbon, oxygen, iron and beyond was created in stars. Fusion in their cores built up elements, and supernova spread them outward. This process, repeated over billions of years, enriched the interstellar medium. Each new generation of stars was born from material that contained more heavy elements than the one before. Our Sun, for instance, formed in a region already enriched by previous supernovae. The planets that formed around it, including Earth, were possible only because earlier stars had lived and died, contributing their contents to the galactic medium. Without the deaths of stars, there would be no rocky planets, no oceans, no life. The variety of stellar deaths creates variety in the galaxy. Planetary nebulae scatter delicate shells of gas, glowing under ultraviolet light. Supernovae carve vast bubbles, shockwaves compressing nearby gas into new stars. Neutron stars and black holes create exotic systems, their gravity pulling on companions, their presence detected in pulses or flares. White dwarfs, though quiet, can explode again under certain conditions. If they accrete matter from a companion and exceed a critical mass, they ignite in a thermonuclear supernova, destroying themselves completely. These Typhoon supernovae are so regular in brightness that they serve as cosmic distance markers. Every kind of stellar death adds something, new elements, new structures, or new phenomena to the galactic story. The cycle of stellar life and death also shapes the appearance of the Milky Way. Spiral arms glow brightly, not only because of newborn stars, but also because of the short-lived giants that end in supernovae, enriching those regions. The bulge at the centre contains older stars, many long past their prime, giving it a different colour and texture. The halo holds ancient stars, survivors from the galaxy's earliest generations. Everywhere you look, the mix of stars at different ages reflects this ongoing process. Our own sun's fate is already written. Billions of years from now, when its hydrogen runs out, it will swell into a red giant. Earth's oceans will boil, its atmosphere stripped, its surface scorched. Eventually the sun will shed its outer layers, forming a planetary nebula. At the centre will remain a white dwarf, glowing faintly as it cools. That remnant will persist long after the planets are gone, a tiny ember carrying the memory of a once bright star. In the distant future, even it will fade into darkness. But by then, the matter the sun contributed will have joined the interstellar medium, ready to become part of new stars, new planets, and perhaps new life. This cycle, repeated billions of times across the Milky Way, is what keeps the galaxy alive. Without it, stars would burn out, and the galaxy would go dark. With it, there is renewal, constant creation balanced by inevitable destruction. It is not a cycle measured in days or years, but in millions and billions of years, vast spans of time that dwarf our experience. Yet by studying it, we gain perspective. We see that the stars we admire are not fixed but dynamic, each one a story in progress, each one contributing to the whole. And so, when you look at the Milky Way, you're not just seeing stars in the present, you're seeing stars at every stage of life. Some just forming in nebulae, some shining steadily on the main sequence, some swelling into giants, some dying in explosions, and some already reduced to remnants. The galaxy is a tapestry woven of these stages, a living system sustained by the births and deaths of its stars. When you look around at the world, it is easy to think of Earth as something separate from the galaxy. The ground beneath your feet, the air you breathe, the water in the oceans, they feel local, belonging to this planet alone. But if you trace their origins back far enough, you discover that none of it began here. The atoms that make up everything around you and everything within you were forged in stars. The calcium in your bones, the iron in your blood, the oxygen you inhale, the carbon that forms the backbone of your cells, all of it came from stellar furnaces and stellar deaths. In that sense, the Milky Way is not just the galaxy we live in. It is also the source of our material existence. We are quite literally made of stardust. This idea, often repeated in simple phrases, carries with it a deep scientific truth. The early universe, in the moments after the Big Bang, produced only the lightest elements: hydrogen, helium, and traces of lithium. Those elements condensed into the first stars. Within their cores, fusion began. Hydrogen fused into helium, helium into carbon, carbon into oxygen, and so on, building heavier and heavier nuclei. Stars became factories, forging elements through nuclear reactions. But stars cannot last forever. When they die, they release those elements into space. Small stars shed their outer layers gently, creating planetary nebulae. Large stars explode violently in supernovae, scattering their contents far and wide. Over billions of years, the Milky Way has been enriched by these processes. The interstellar medium now contains not just hydrogen and helium, but the full periodic table, recycled through countless generations of stars. Every cycle of star birth and death adds more complexity to the galaxy. Early generations produced mostly helium and traces of carbon and oxygen. Later generations added iron, silicon, sulfur, and dozens of other elements. Today, the gas and dust in nebulae are rich enough to form rocky planets, atmospheres, oceans, and eventually life. Without this recycling, the universe would remain a place of gas and stars, with no solid ground, no chemistry complex enough for biology. The story of life on Earth is inseparable from the story of cosmic recycling. Consider the iron that flows in your bloodstream. Those atoms were created in the core of a massive star. When that star reached the end of its life, unable to fuse iron further, it collapsed and exploded. The blast scattered iron into space, where it drifted for millions of years until it became part of a molecular cloud. From that cloud, our solar system formed. Planets condensed, Earth took shape, and eventually organisms evolved that made use of iron in their blood to carry oxygen. Every heartbeat you feel is powered by atoms that once lay inside a star. The oxygen you breathe has a similar story. It too was formed in stars created by fusion of helium and carbon. Supernovae expelled it into space, mixing it with other elements. When Earth formed, oxygen became part of its crust, oceans and atmosphere. Over time, life adapted to use it for metabolism, building it into the chemistry of cells. Every breath you take links you to stars long gone. Carbon, the basis of organic molecules, was also forged in stars. It forms in a delicate process known as the triple alpha reaction, where 3 helium nuclei combine under extreme heat and pressure. That process happens in the cores of aging stars, and when those stars shed their outer layers, carbon is carried outward into space. Without that stellar contribution, there would be no carbon chains, no proteins, no DNA, no life. The fact that carbon exists in abundance is the direct result of billions of years of stellar evolution. Even the gold in a wedding ring, or the uranium in the Earth's crust, has a cosmic origin. These heavy elements are not formed in ordinary fusion but in more extreme events. such as supernovae or collisions of neutron stars. When two neutron stars merge, the explosion, known as a kilonova, produces enormous amounts of heavy elements, scattering them into space. These rare but powerful events seed the galaxy with elements heavier than iron. The jewellery people wear, the fuel deep within the Earth, the rare metals in electronic devices, all trace their lineage to such cosmic cataclysms. This recycling process has been going on for billions of years, gradually enriching the galaxy. Astronomers measure the composition of stars and can tell their relative ages by how much heavy element content they contain. Older stars, formed early in the galaxy's history, are poor in heavy elements. Younger stars, like the Sun, have more. This metallicity, as astronomers call it, is a record of recycling. It shows how the Milky Way has matured, how it has evolved from a simple system of hydrogen and helium into a complex environment capable of supporting planets and life. The solar system itself is a product of this process. About 4.6 billion years ago, a cloud of gas and dust, already enriched by generations of stars, collapsed to form the Sun. Around it, a disk of leftover material coalesced into planets. Rocky worlds like Earth formed from heavier elements, while lighter gases collected into giants like Jupiter. Comets and asteroids preserved primitive material, carrying the chemical signatures of the early solar system. Every part of the system, from the gas giants to the smallest moon, owes its existence to the recycling of stardust. On Earth, the connection is especially intimate. Life depends on elements forged in stars, and life itself participates in recycling. Plants take carbon from the atmosphere, incorporate it into tissues, and pass it along to animals that eat them. When organisms die, their matter returns to the soil and air, eventually incorporated into new life. The cycle continues on scales both small and large, echoing the cosmic cycle of stars. The Milky Way recycles matter into stars and planets. Earth recycles matter into living forms. Both cycles are linked, one nested inside the other. This perspective changes how we see ourselves. It is easy to think of humanity as separate, as unique to Earth, but in truth, we are expressions of galactic chemistry. Our bodies are assemblies of atoms made in stars, arranged by biology into tissues and organs. When we die, those atoms will return to the Earth, and eventually, over immense spans of time, they may return to the galaxy. Some atoms that were once part of living beings on Earth will one day drift into space, carried away by the Sun when it becomes a red giant. They may become part of future clouds, future stars, and future planets. In that sense, our story is not isolated, but part of a much larger narrative. Astronomers sometimes say that we are a way for the universe to know itself. This is not only a poetic idea, but a literal one. The universe has produced stars, stars have produced elements, elements have produced planets, and on at least one of those planets, those elements have combined into life capable of reflection. The atoms that make thought possible were once inside stars. By recycling them, the galaxy has made it possible for matter to become conscious, to ask questions, and to recognize its own origins. The phrase, "we are stardust," can sound abstract, but it is not. It is a direct statement of physical fact. Every element heavier than helium in your body was made in a star. The hydrogen atoms in the water you drink date back to the Big Bang itself, billions of years ago. The oxygen and carbon in that water were made in stars that lived and died long before the Sun was born. The iron in your hemoglobin was cast into space by a supernova. The calcium in your bones came from a dying star shedding its outer layers. You are a collection of recycled atoms, gathered temporarily into a form that thinks and feels. Even now, the recycling continues. Stars are still being born in nebulae, using the enriched material scattered by previous generations. They will live, shine, and die, contributing again to the medium. The Milky Way is an ongoing experiment in transformation. The cycle will not stop with us. Long after Earth is gone, Long after the sun has faded, the matter that once made up this world will remain in the galaxy, taking on new forms. Perhaps some of those atoms will one day be part of another planet, circling another star where life will arise again. To think of recycling on such scales is to see continuity where we often imagine finality. Death of a star is not the end, it is the beginning of enrichment. Death of a planet or a living being is not the end of matter, only its rearrangement. The galaxy is a recycler, conserving atoms, reusing them endlessly, writing new stories with old ingredients. Each new star is built from the ashes of many that came before. Each new planet is assembled from debris of previous generations. Each new life form is constructed from atoms that have been part of countless other things. The Milky Way is not static. It breathes in cycles of creation and destruction. Stars ignite, live, and die, scattering their contents. Clouds gather, collapse, and form new stars. The galaxy recycles itself continuously. And through that process, it has given rise to beings capable of seeing the stars, capable of realizing their connection to them. That realization is a product of recycling, a byproduct of the long chain of transformations that turned hydrogen into life. So the next time you look up at the Milky Way, consider not only the stars shining there, but also the unseen cycle behind them. Each star is both a product and a contributor. Each one will eventually return its matter to the medium, and that matter will become part of something new. The galaxy is a recycler, and we are part of its cycle. Our very existence is proof of its continuity. When you think of the Milky Way, it is tempting to picture it as an isolated island of stars floating alone in the dark. But galaxies are rarely solitary. They're often surrounded by companions, large and small, some orbiting closely, others drifting farther away, yet still bound by gravity. Our galaxy too has neighbours. Some are vast systems like the Andromeda galaxy, preparing for a future encounter with us. Others are smaller, faint, and easily overlooked, yet they circle us like satellites. Still others are not full galaxies but groups of stars within the Milky Way itself, clusters that formed together and have remained bound for millions or even billions of years. These companions and groupings near and far give the Milky Way its social life. They are its galactic neighbours. One of the most striking features of the galaxy is the presence of star clusters. Unlike the scattered stars you see in constellations, which only appear grouped from our perspective, clusters are real associations. Their stars were born from the same cloud at the same time, and they share a common origin. There are two main kinds: open clusters and globular clusters. Open clusters are younger, looser groups of a few dozen to a few thousand stars. They are found mostly in the disk of the galaxy, especially in the spiral arms, where star formation is active. Globular clusters are older, denser, and far more massive, containing hundreds of thousands of stars packed into tight spheres. They inhabit the halo, orbiting the galaxy like ancient satellites. Open clusters are perhaps the easiest to see with the naked eye. The Pleiades, often called the Seven Sisters, is one of the most famous. Located in the constellation Taurus, it appears as a small group of bright stars, easily visible even from cities with moderate light pollution. Through binoculars, dozens more stars appear, all bound together loosely. The cluster is only about 100 million years old, making it a baby by stellar standards. It will not remain bound forever. Over time, gravitational interactions with other stars and the tidal pull of the galaxy will scatter its members. Eventually, the Pleiades will dissolve, its stars drifting off into the disk, indistinguishable from the rest. This fate awaits most open clusters. They are temporary groupings, transient associations that eventually disperse. Another example is the Hyades, also in Taurus. It is older than the Pleiades, about 600 million years, and more spread out. Its stars form a distinctive V shape that outlines the face of the bull. Like the Pleiades, it will eventually disperse. Open clusters are valuable to astronomers because their shared age and composition provide benchmarks for studying stellar evolution. By comparing their stars, scientists can test theories of how stars age, how they shine, and how they change over time. Each cluster is like a laboratory, offering a snapshot of stellar life at a particular moment. Globular clusters, by contrast, are much older and far more enduring. The Milky Way has around 150 of them, orbiting in the halo like bees around a hive. They are ancient, with ages of 10 to 13 billion years, nearly as old as the galaxy itself. Their stars are metal poor, meaning they contain few heavy elements, a sign that they formed early before the galaxy had been enriched by many generations of stellar death. Globular clusters are dense, with stars packed so tightly that in their cores the night sky would be ablaze with light. From Earth, they appear as fuzzy balls through small telescopes, but larger instruments resolve them into swarms of stars, hundreds of thousands glittering together. One of the most famous is Omega Centauri, visible from the southern hemisphere. It contains several million stars and may once have been the core of a dwarf galaxy captured by the Milky Way. Another is M13, the Great Hercules Cluster, visible from the northern hemisphere. Through a telescope, it reveals a breathtaking globe of stars, each one a sun, all orbiting together in a gravitational embrace. Globular clusters are survivors. While open clusters dissolve over time, globulars remain intact for billions of years. Their presence tells us about the early history of the Milky Way, offering clues to how it formed and grew. Beyond clusters, the Milky Way has larger companions, satellite galaxies. These are smaller galaxies bound to us by gravity orbiting in the halo. The most prominent are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as faint smudges of light. These irregular galaxies are close neighbours, only about 160,000 and 200,000 light-years away respectively. They are actively forming stars, and their interaction with the Milky Way stirs streams of gas between them. The Magellanic Clouds are among the closest galaxies to us, and their proximity allows astronomers to study star formation and galactic dynamics in detail. Other satellite galaxies are fainter, harder to see. The Sagittarius dwarf galaxy, discovered in the 1990s, is in the process of being torn apart by the Milky Way's gravity. Streams of its stars arc across the sky, evidence of its merger into the larger system. The Canis Major dwarf galaxy, even closer, may also be dissolving. In total, dozens of small satellite galaxies orbit the Milky Way, many so faint they were only discovered in recent decades. These dwarf galaxies are relics, survivors from the galaxy's early environment, slowly accreted into the larger whole. Their stars add to our halo. Their orbits trace the complex history of mergers and growth. The presence of these neighbours shows that the Milky Way is not static, but still growing. Galaxies evolve by consuming smaller companions, and the streams of stars in our halo are fossil records of those events. Each cluster, each satellite, tells part of the story of how the galaxy assembled itself. Some of the globular clusters may have originated in dwarf galaxies now long gone, stripped of their stars and absorbed. The halo is full of such evidence, written not in words but in orbits, trajectories and chemical compositions. The local group, the collection of galaxies to which the Milky Way belongs, is dominated by three large members: the Milky Way, Andromeda, and the Triangulum galaxy. Around these giants are dozens of dwarfs, satellites orbiting in complex patterns. Our galaxy's companions are part of this larger group, and their interactions with us are shaped by the gravity of the group as a whole. The Milky Way is not isolated, but part of a cosmic neighbourhood, and its satellites are its immediate family within that neighbourhood. Thinking about galactic neighbours also changes how we view the night sky. When you see the Pleiades, you are seeing a star cluster, siblings bound together. When you see Omega Centauri through a telescope, you are seeing one of the largest globular clusters, a survivor from the galaxy's earliest days. When you look south and spot the Magellanic Clouds, you are seeing whole galaxies, companions orbiting ours. These are not distant curiosities, but immediate neighbours, part of the Milky Way's extended structure. Our solar system, in its quiet spur, is surrounded by these neighbours, though their presence is not obvious. They orbit silently, slowly, their paths taking millions of years. Yet they are there, and they influence the galaxy's evolution. Streams from disrupted dwarfs add stars to the halo. Gas flows from satellites feed the disk. Globular clusters shape the motions of stars as they pass through. The Milky Way is not only the sum of its stars and arms, but also the sum of its companions and clusters. In a sense, the galaxy's neighbours remind us that nothing in the universe is truly alone. Just as Earth has its moon, just as the Sun has its planets, so the Milky Way has its clusters and satellites. Each level of structure is part of a hierarchy, bound by gravity interacting over time. From the smallest scale to the largest, the universe is social, built of relationships. The Milky Way's neighbours are part of that pattern, companions in its long journey through space. And as the galaxy moves forward, those neighbours will continue to play their roles. Some will merge fully, their stars blending into ours. Some will remain as satellites circling indefinitely. Clusters will survive or dissolve, depending on their density and environment. The story of the Milky Way is not only about its own stars, but also about those it carries with it, those that orbit alongside it, and those it consumes. Its neighbours are part of its identity, shaping its past and its future. When astronomers first set out to understand the Milky Way, they expected the visible stars, gas and dust to explain its behaviour. After all, what we see appears to be what is there. But as they measured the motions of stars, especially those far from the centre, a puzzle emerged. According to Newtonian physics, the farther a star is from the galactic centre, the slower it should orbit. Just as planets in the solar system follow that rule, with Mercury moving quickly around the Sun, while Neptune creeps more slowly along, the same pattern was expected for stars in the Milky Way. Yet when those motions were studied carefully, the outer stars did not slow down as expected. Instead, they orbited at nearly the same speed as stars much closer in. Something was missing from the picture, something unseen, providing extra gravity to hold the stars in place. That unseen something became known as dark matter. Dark matter is one of the great mysteries of modern astronomy. It does not shine, reflect, or absorb light. No telescope, no matter how powerful, can see it directly. Yet its effects are everywhere. In the Milky Way, it forms a vast halo surrounding the visible disk. This halo extends far beyond the luminous part of the galaxy, reaching out hundreds of thousands of light years. Within it, dark matter outweighs ordinary matter by a factor of 5 or more. That means most of the Milky Way's mass is invisible, made of something we cannot yet detect except through its gravitational pull. The idea of dark matter dates back nearly a century. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster of galaxies and found that the galaxies were moving too quickly to be held together by their visible mass. He proposed the existence of dunkel Materie, dark matter, to explain the missing mass. At the time, the idea was radical and largely ignored. But decades later, studies of spiral galaxies, including the Milky Way, revived the concept. Vera Rubin and Kent Ford in the 1970s measured the rotation curves of galaxies and found the same unexpected pattern. Stars far from the centre orbited just as fast as those closer in. The conclusion was unavoidable. There had to be much more matter than what was visible. In the Milky Way, the presence of dark matter is inferred from similar evidence. Without it, the outer stars would not orbit at their observed speeds. The galaxy would fly apart, its disk unable to hold together. With it, the rotation curve makes sense. The halo of dark matter provides the extra mass needed to explain the motions. This halo is not confined to the disk or bulge, but envelops the entire galaxy, an invisible scaffold on which the Milky Way is built. What exactly dark matter is, however, remains unknown. It is not made of ordinary atoms. If it were, we would detect it in the form of faint gas or dust. Instead, it seems to be a different form of matter entirely, made of particles that interact weakly with light and with ordinary matter. Many candidates have been proposed, from weakly interacting massive particles, WIMPs, to axions to sterile neutrinos. Experiments on Earth, deep underground and in particle accelerators, are searching for signs of these particles, but so far no detection has been confirmed. Dark matter remains a hypothesis supported by overwhelming indirect evidence but still lacking direct proof. Despite its mystery, dark matter is essential to the Milky Way structure. It shapes the galaxy's formation and evolution. In the early universe, tiny fluctuations in the distribution of dark matter grew under gravity, forming clumps that pulled in gas and dust. These clumps became the seeds of galaxies. Without dark matter, the universe would not have had enough time to form galaxies as we see them today. The Milky Way itself owes its existence to the framework provided by dark matter. It is not just an add-on to the visible galaxy, but the foundation on which everything rests. The halo also explains the distribution of satellites and clusters around the Milky Way. Dwarf galaxies and globular clusters orbit within the dark matter halo, their paths influenced by its mass. Some of these satellites may even be embedded in their own sub-halos of dark matter, nested within the larger structure. The streams of stars observed in the halo, remnants of past mergers, are shaped by the gravitational field of dark matter. To study them is to map the invisible. The size of the halo is immense. While the visible disk of the Milky Way is about 100,000 light-years across, the halo may stretch 10 times farther. That means the galaxy, in its full extent, is vastly larger than the stars and gas we see. When you look up and trace the band of the Milky Way, you're seeing only the luminous part, a thin layer within a much larger sphere of unseen matter. The true boundary of the galaxy is defined not by light, but by gravity, and gravity extends as far as the halo. Dark matter also affects the future of the Milky Way. The coming collision with Andromeda, for instance, will not be just a meeting of visible stars and gas, but also a merging of halos. The dark matter of both galaxies will overlap, pulling them together long before the stars themselves collide. The eventual result will be a new, larger galaxy, shaped by the combined mass of their halos. Without dark matter, the dynamics of that encounter would be very different. With it, the outcome is set by invisible hands. The search for dark matter continues on many fronts. Astronomers study the motions of stars in the outer halo, looking for clues about its shape and distribution. Some evidence suggests the halo may not be perfectly spherical, but elongated or lopsided, shaped by interactions with satellites. Others look for subtle effects of dark matter on the cosmic microwave background, the afterglow of the Big Bang. Physicists build detectors to catch rare interactions between dark matter particles and ordinary matter, hoping for a direct detection. Each experiment brings us closer, but the mystery remains unsolved. What is clear is that the halo is not empty. It is the dominant form of mass in the galaxy. It holds the stars in place, shapes their orbits, guides the formation of clusters and satellites, and ensures the Milky Way remains coherent. Without it, the galaxy would be a fragile thing, scattered by its own rotation. With it, the galaxy is stable, enduring across billions of years. It's a strange thought that most of the Milky Way is invisible. The stars, nebulae, and clusters that dazzle us are only a small fraction of its substance. The rest lies hidden, detectable only through its influence. Yet that hidden matter is what allows the visible parts to exist as they do. The Milky Way is a galaxy of light built on a foundation of darkness. Its halo is the unseen architecture, the silent mass that holds everything together. When you think of the Milky Way, remember that what you see is only part of the whole. The spiral arms, the glowing nebulae, the dense clusters, and even the central black hole are all embedded in a much larger halo of dark matter. It is mysterious, invisible, and still not understood, but it is real. It is the unseen framework of our galaxy, the hidden mass that makes the Milky Way what it is. When you stand beneath a clear night sky, the stars seem fixed, as if they are part of a grand celestial dome that never changes. For thousands of years, people assumed the heavens were unmoving, eternal. But nothing in the universe is truly still. Every star you see is in motion, tracing its path around the centre of the Milky Way. The galaxy itself is also moving, carried through space by the gravitational pull of larger structures. Our solar system, Earth included, is not anchored in a stationary sky, but travelling as part of a vast cosmic flow. The Milky Way is not only rotating on its own axis, but drifting, pulled, and nudged by other galaxies and invisible matter. To understand our home fully, we have to recognise not only its internal motions, but also its place in the wider universe. Inside the galaxy, we orbit the centre at a speed of more than 800,000 kilometres per hour. That orbit is part of the grand rotation of the Milky Way, with stars at different distances moving at different rates. Yet beyond this internal spin, the entire galaxy is moving relative to its surroundings. Astronomers measure this motion by looking at the cosmic microwave background, the faint afterglow of the Big Bang spread evenly across the universe. Against that backdrop, the Milky Way shows a measurable drift, a sign that our galaxy, along with all its stars, is not fixed but streaming through space. Relative to the cosmic microwave background, the Milky Way is moving at about 600 kilometers per second. That's more than 2 million kilometers per hour. At such speeds, the galaxy could cross the distance from Earth to the Moon in less than 7 minutes. Of course, space is vast, so these motions unfold slowly from our perspective. Yet on cosmic scales, the Milky Way is covering immense distances, its trajectory shaped by the gravitational pull of nearby structures. One of the main influences on our motion is the Andromeda galaxy. Located about 2.5 million light-years away, Andromeda is the nearest large spiral galaxy to us, and it is on a collision course. Both galaxies are part of the Local Group, a collection of more than 50 galaxies bound together by gravity. Within this group, the Milky Way and Andromeda dominate, their mutual attraction pulling them closer. Measurements show that Andromeda is approaching at about 110 kilometers per second. In about 4 billion years, the two galaxies will collide and eventually merge, forming a new, larger galaxy. This future encounter is one of the defining features of the Milky Way's motion. We are not just drifting randomly through space. We are headed for a meeting that will reshape our galactic identity. Beyond Andromeda, the Local Group itself is moving as part of an even larger structure. We are located on the edge of a region known as the Virgo Cluster, a massive collection of galaxies. The Local Group is being drawn toward the cluster, influenced by its gravity. Farther still, the Milky Way is being pulled toward an enormous region called the Great Attractor, located hundreds of millions of light-years away in the direction of the constellations Hydra and Centaurus. This gravitational anomaly, part of a supercluster of galaxies known as Laniakea, exerts a pull on our galaxy and many others. The Milky Way is not isolated. It is part of a flow of galaxies, all moving toward denser regions of the universe, like rivers converging into a sea. These motions are invisible to the eye but measurable through careful observation. Astronomers track the Doppler shifts of galaxies, the changes in wavelength of their light caused by motion. By compiling measurements from many galaxies, they map the flow of matter on cosmic scales. The result is a picture of a universe where everything is moving, not only because of cosmic expansion, but also because of local gravitational pulls. The Milky Way is one participant in this grand ballet, circling, drifting, and streaming through the cosmic web. It's important to recognise that our motion does not affect our daily experience. On Earth, gravity keeps us firmly attached to the planet. The solar system moves as a unit, so we do not feel the speed. It is only when we measure carefully, looking outward, that we realise how fast we are travelling. In that sense, our journey through space is both ordinary and extraordinary. Ordinary, because it has always been happening, unnoticed. Extraordinary, because when we calculate the numbers, the scales are staggering. the galaxy's motion also influences its shape and structure. As we move through intergalactic space, we encounter smaller galaxies and streams of matter. The Milky Way has absorbed many such companions over its history. Evidence of past mergers can be seen in the stellar streams in the halo, long arcs of stars pulled from disrupted galaxies. These mergers are part of the Milky Way's growth, a direct result of its motion through a crowded cosmic neighbourhood. The stars above us include not only those born here, but also immigrants from smaller galaxies consumed long ago. Our motion shapes our identity, enriching the galaxy with diversity. Looking ahead, the most dramatic effect of our motion will be the merger with Andromeda. When the two galaxies collide, stars will not smash into each other. The distances between them are too vast, but their gravitational interactions will reshape orbits, distort structures, and trigger bursts of star formation. The Milky Way's spiral arms may be torn apart, and new structures may emerge. Over time, the two galaxies will settle into a single, massive elliptical system. Our solar system will be carried along, perhaps flung into a different orbit, but still bound to the new galaxy. This future is written into our motion, inevitable over billions of years. Beyond Andromeda and the local group, the Milky Way's trajectory is part of even larger patterns. The universe itself is expanding, carrying galaxies away from each other on the grandest scales. But locally, gravity overrides expansion, pulling galaxies together into clusters and superclusters. Our motion toward the Great Attractor is one example of this. It is as though space itself is stretching, yet pockets of mass resist, drawing matter inward. The Milky Way's journey is a small part of this larger cosmic flow, but it connects us to structures hundreds of millions of light-years across. To picture the Milky Way's motion, imagine floating in a river. The current carries you along, sometimes swiftly, sometimes slowly, depending on the shape of the riverbed. Other objects drift beside you, some closer, some farther, all carried by the same flow. Occasionally, currents converge, pulling objects together into whirlpools. The Milky Way is like that, carried by gravity, influenced by neighbours, pulled toward denser regions. Its path is not random, but shaped by the contours of the universe's mass. When you look up at the sky tonight, the stars may seem fixed, but each one is moving, and the galaxy itself is moving with them. Over eons, the constellations will change, Andromeda will grow closer, and the larger structures of the universe will shift subtly. The Milky Way's motion reminds us that stillness is an illusion. On every scale, from Earth's rotation to the galaxy's drift, we are travellers, part of a cosmic journey that never stops. When we look toward the constellation of Andromeda on a clear night, what we see is a faint blur, just at the edge of naked eye visibility. Through binoculars or a telescope, the blur resolves into a grand spiral galaxy, tilted toward us, glowing softly from the combined light of 1 trillion stars. It may not look like much to the eye, but that galaxy is the Milky Way's nearest large neighbour. It is also our future. The Andromeda galaxy, also called M31, is not drifting away like most galaxies in the expanding universe. Instead, it is moving toward us, closing the gap at a speed of about 110 kilometers per second. In cosmic terms, it is on a direct collision course with the Milky Way. This future merger is not a matter of speculation. Careful measurements of Andromeda's light show the telltale Doppler shift of approach. For decades, astronomers wondered whether the two galaxies might pass by each other rather than collide. But more recent observations, including data from the Hubble Space Telescope, have confirmed that a collision is inevitable. The question is not if, but when. The answer is that in about 4 billion years the two galaxies will meet, beginning a process that will last another 2 billion years before they settle into a single new system. When people hear collision of galaxies, it is easy to imagine stars crashing into one another, fiery impacts ripping systems apart. The reality is far more subtle. Stars are incredibly small compared to the distances between them. If the Sun were the size of a marble, The next nearest star would be another marble dozens of kilometres away. That means when the Milky Way and Andromeda merge, the stars themselves will almost all pass by without direct collisions. Instead, what will collide are the galaxy's gravitational fields. The mutual pull will distort their shapes, drawing out long tidal tails of stars, warping arms, and mixing populations. Clouds of gas will slam into one another, compressing and triggering bursts of star formation. Over time, the graceful spirals of both galaxies will unravel, replaced by a more rounded, elliptical form. The first encounter will be dramatic. As the galaxies approach, the halos of dark matter will overlap long before the visible disks touch. This gravitational interaction will begin to tug at stars, altering orbits. Eventually, the disks themselves will pass through one another. The Milky Way may develop long tidal streams, ribbons of stars stretched across the sky. Andromeda's structure will distort, its spiral arms twisted and drawn out. From Earth's perspective, if Earth still exists then, the night sky would change in astonishing ways. Andromeda, already visible as a faint smudge, would grow brighter and larger over millions of years. At some point, it would dominate the sky, filling it with a glowing mass of stars. The view would be unlike anything ever seen by human eyes. As the galaxies continue their dance, they will swing past each other and then fall back together. This back and forth interaction will last for billions of years, gradually bleeding away orbital energy as stars and gas are redistributed. Each pass will bring more distortion, more mixing. Eventually, the two galaxies will no longer be separate entities but one combined system. Astronomers sometimes call the eventual product Milkomeda or Milkdromeda, a playful merging of names. The final galaxy will likely be elliptical, a giant ball of stars rather than a flat spiral. Such galaxies are common in the universe, often formed from mergers like this. The fate of the solar system in this merger is uncertain. It will almost certainly survive the process, since the odds of a direct collision with another star are vanishingly small, but its orbit around the galactic centre may change dramatically. Simulations suggest the solar system could be flung into a new orbit, perhaps farther from the centre, perhaps closer, perhaps even ejected into the halo. For Earth itself, if it still exists, the skies would transform. Constellations would dissolve as nearby stars shift. New patterns would form, unfamiliar to any observer used to the night sky of today. The collision would not be destructive on a planetary scale, but it would rewrite the stellar backdrop completely. The gas within the galaxies will tell another story. When clouds collide, they compress, igniting intense bursts of star formation. These starbursts will create clusters of massive, short-lived stars that shine brilliantly before dying in supernovae. The merger will therefore be a period of both creation and destruction. Creation of new stars, destruction of old galactic structures. Over time, the gas will be used up or heated so much that further star formation slows. The resulting galaxy, though massive, may eventually settle into a quieter phase, with older stars dominating and fewer new ones forming. The role of dark matter in this process is central. The halos of the Milky Way and Andromeda will merge first, their invisible mass pulling the galaxies together. The distribution of this dark matter will shape the details of the collision, guiding how stars are redistributed and how the final structure forms. It is a reminder that even in the most spectacular visible events, the unseen framework of the universe plays the decisive role. This coming collision also places the Milky Way in context. We are not a permanent spiral galaxy. We are in a stage of life, one that will eventually give way to another form. Just as stars evolve, galaxies evolve too. Spirals merge into ellipticals. Ellipticals may accrete new material, and the cycle continues. The Milky Way is not fixed but part of a cosmic narrative, shaped by its interactions with neighbours. The future with Andromeda is part of that story, as inevitable as the aging of stars. If life endures long enough to witness the merger, the view would be beyond imagination. Imagine standing under a sky where a second galaxy rises alongside the Milky Way, growing larger with each passing million years until the two swirl together in a brilliant display of light. Imagine constellations shredded and replaced, star clusters forming in bursts, tidal tails of stars stretching across the heavens. For any beings alive then, the sky would be a living demonstration of cosmic evolution. The slow ballet of galaxies, invisible to us now except through telescopes, would become a visible fact of existence. But even if no one is there to watch, the process will unfold. Galaxies do not need witnesses. They follow the laws of gravity, their fates written in their motions. The Milky Way and Andromeda are destined to merge, and in doing so they will become something new. The spiral arms we know today will be gone, replaced by a different form, yet the stars will remain, the planets will remain, and the new galaxy will shine as a massive elliptical, carrying forward the combined histories of both. In a way, this collision is part of the universe's creativity. Just as stars die and seed new generations, just as nebulae collapse into new suns, so galaxies merge and create new structures. Nothing remains unchanged. Everything is part of a cycle of transformation. The Milky Way's future with Andromeda is simply the next step in that larger pattern. When you think of the Milky Way, it is natural to picture it as a definite object, a structure with a beginning and an end, like a city on a map or an island in the sea. We imagine spiral arms curving gracefully outward, a central bulge shining with old stars, and beyond that, a boundary where the galaxy stops and the void of intergalactic space begins. But galaxies are not like islands with clear shorelines. Their edges are diffuse, fading gradually into darkness. The question of where the Milky Way ends is not simple to answer. It depends on what you mean by end. Is it the point where the last star orbits? Where the gas thins out? Where the influence of gravity fades? Each answer reveals something different about the structure of our galaxy. To the eye, the Milky Way seems to end at the edges of the bright band you see in the night sky. That glowing river of stars is the disk, about 100,000 light-years across. Most of the galaxy's stars are located here, concentrated in a thin plane only 1,000 light-years thick. If you define the galaxy only by its luminous disk, then you could say it ends there, in a flat circle of stars, dust and spiral arms. But that is just the beginning. Beyond the disk there are more stars, faint and sparse, scattered in a halo that surrounds the galaxy. These halo stars stretch far beyond the disk, extending the galaxy's reach by tens of thousands of light-years. The halo is not as obvious as the disk, but it is still part of the Milky Way. Within this halo are globular clusters, ancient groups of stars that orbit the galaxy on long, looping paths. Some of them are more than 200,000 light-years from the centre, far beyond the visible disk. These clusters mark one kind of boundary. The outermost stellar population still gravitationally bound to the Milky Way. Beyond them, the stars grow fewer, blending eventually into intergalactic space. Yet even there the galaxy's influence persists. Gravity does not stop at a sharp line. It fades gradually, weakening with distance but reaching indefinitely. And then there is dark matter. As we have seen, the visible stars are only a fraction of the Milky Way's mass. The galaxy is enveloped in a vast halo of dark matter, invisible but real, extending perhaps 10 times farther than the disk. This halo may reach out to nearly 1 million light-years from the centre, half the distance to Andromeda. If you define the galaxy by the reach of its dark matter, then the Milky Way's edge is unimaginably vast. By that definition, our galaxy and Andromeda already overlap, their halos blending into one another. The idea of an edge becomes even less clear, more like a gradual merging than a sharp boundary. The question of the galaxy's end also depends on how you think about motion. Stars in the disk orbit the centre in regular patterns, but in the halo, orbits become less ordered. Some stars are bound tightly, while others are barely clinging, moving so fast and so far that they skirt the limits of the galaxy's pull. At some distance, gravity loses its grip entirely, and stars drift into intergalactic space. That distance, called the virial radius, is one way astronomers define the edge. For the Milky Way, estimates put it around 250,000 to 300,000 light-years. Within this radius, the galaxy's gravity dominates, binding stars, gas, and dark matter into a single system. Beyond it, the influence of other galaxies, particularly Andromeda, becomes more important. The gas in the Milky Way also stretches farther than you might think. Hot, diffuse hydrogen has been detected hundreds of thousands of light-years from the disk, forming a corona of ionized gas. This halo of gas may contain as much mass as all the stars in the galaxy, though it is spread thinly across enormous volumes. It is invisible to the eye but detectable in ultraviolet and X-ray observations, especially where it absorbs light from background quasars. This gaseous halo represents another layer of the galaxy's extent, a reminder that the Milky Way is not just stars and arms but also an envelope of matter reaching far outward. From Earth's perspective, defining the edge is even more complicated because we are inside the galaxy. Looking outward, we see stars fade with distance, but our line of sight is blocked by dust and limited by instruments. Mapping the farthest regions requires careful measurements, parallax data from satellites like Gaia, and the detection of faint distant clusters. Each improvement in technology extends our sense of where the Milky Way ends. The more we look, the more diffuse it becomes, as though the galaxy resists being pinned down. And then there is the philosophical side of the question. Does the galaxy end where its visible components fade, or does it end where its influence ends? If you think of the Milky Way as only its stars, then it has a finite edge, somewhere beyond the halo. If you think of it as all the matter gravitationally bound to it, including dark matter and gas, then its edge is much farther. If you think of it as a structure within the cosmic web, connected by filaments of dark matter and gas to other galaxies, then perhaps it has no true edge at all. It is part of a larger continuum, a node in the vast network of the universe. The difficulty of defining the edge reflects the nature of galaxies themselves. They are not rigid objects but dynamic systems, shaped by interactions, accreting matter and losing stars. The Milky Way is currently absorbing dwarf galaxies, pulling their stars into streams that wrap around the halo. Some of those stars are already beyond the traditional boundaries, yet they are part of the galaxy's story. The edge is not fixed but evolving as the galaxy grows and changes. For us, though, the question of the edge has a practical side. Knowing where the Milky Way ends helps astronomers measure its mass, compare it to other galaxies, and understand its role in the local group. It tells us how much matter is available for future star formation, how much gas lies in the halo, and how the galaxy interacts with its neighbours. The edge is not just a philosophical boundary but a scientific one, helping us place the Milky Way in context. Still, the image of the galaxy as an island persists, and it is not entirely wrong. Within the vast universe, the Milky Way is a distinct system, with its own stars, gas and dark matter, separated from others by expanses of space. Like an island with a coastline that blurs into the sea, the galaxy has a boundary that is not sharp but real enough. It is a place where the density of stars drops, where the influence of gravity wanes, where the light fades into darkness. Beyond it lies intergalactic space, dotted with other islands, each with its own uncertain edge. When you think of the edge of the galaxy, imagine standing on a shore at night, looking out across a dark ocean. The land behind you is solid, full of life and light. Ahead is water, endless and dark, merging with the sky. The line between land and sea is not precise. It shifts with the tide, blurs with the mist, but you know it is there. The Milky Way's edge is like that, a boundary that fades gradually but still marks the transition from one domain to another. We are creatures who like definitions, but the galaxy offers only gradients, shades of belonging that stretch outward until they vanish into the larger whole. And so, when we ask where the Milky Way ends, the best answer is that it depends on what you are measuring. The disk ends around 50,000 light-years from the centre. The halo of stars extends 2 to 3 times farther. The gas halo stretches beyond that, perhaps to 300,000 light-years. The dark matter halo goes farther still, maybe to 1,000,000 light-years. Beyond that, gravity blends with that of Andromeda, and the two galaxies share their space. The edge is not a single line, but a series of layers, each revealing a different truth. For us, standing on a planet 27,000 light-years from the galactic centre, these scales are difficult to grasp. The Milky Way is already immense in our sky, yet most of it is invisible to us. The edge is out there, far beyond what we can see, fading into the cosmic ocean. Perhaps that is the most important lesson, that the galaxy is larger than we imagine, that its boundaries are not fixed, and that our place within it is part of a continuum rather than an enclosure. The Milky Way ends, and it does not end, both at once, depending on how you choose to see it. From the surface of our planet, the Milky Way appears as a band of light, soft and diffuse, stretching across the sky. To ancient eyes it was a mystery, interpreted in myths and stories. To modern astronomy, it is a subject of study, mapped and measured with growing precision. Yet despite our progress, we are still bound to Earth, peering outward from within the galaxy. Exploring the Milky Way is unlike exploring a continent or an ocean. We cannot sail across it or fly above it. Instead, we must learn from light, from radiation, from careful observation that turns the sky into a map of extraordinary detail. The first step in exploring the galaxy was simply recognizing what the Milky Way is. For centuries, it was thought to be a cloud or a celestial river. Only with the invention of telescopes did it become clear that the band of light is made of countless stars. Galileo, turning his telescope to the Milky Way in the early 1600s, saw the haze resolve into individual points. What had seemed like mist was revealed as a multitude. From that moment, the galaxy began to shift from myth to science. In the 18th and 19th centuries, astronomers tried to map the Milky Way structure by counting stars. William Herschel and his sister Caroline made systematic surveys, recording thousands of stars to estimate the shape of the galaxy. Their maps suggested a flattened disk with the Sun near the centre. Later work refined that view, showing that the Sun is actually offset, about 27,000 light-years from the galactic core. Even without leaving Earth, patient observation allowed astronomers to sketch the outlines of our home. As technology advanced, new wavelengths of light opened new windows. Radio astronomy, beginning in the 1930s and flourishing after World War II, revealed the distribution of hydrogen gas across the galaxy. Neutral hydrogen emits radiation at a wavelength of 21 centimeters, which can pass through dust that blocks visible light. By mapping this signal, astronomers traced the spiral arms of the Milky Way, confirming its overall structure. For the first time, we had a way to see beyond the obscuring dust of the disk. Infrared astronomy extended that reach. Dust absorbs and scatters visible light, but it glows in the infrared. Space telescopes like IRAS, Spitzer and WISE mapped the galaxy in this range, showing structures hidden from view. Infrared light revealed star-forming regions, embedded in clouds, invisible in optical telescopes. It also mapped the crowded centre of the galaxy, where dust is thickest. Suddenly the hidden heart of the Milky Way became visible, not in photographs taken by spacecraft travelling there, but from the careful collection of light here on Earth. X-ray and gamma-ray astronomy opened even more extreme perspectives. These high-energy ranges show the activity of black holes, neutron stars, and supernova remnants. Observatories like Chandra and Fermi detected bursts and flares from the galactic centre, radiation from matter spiralling into Sagittarius A. They also revealed diffuse emissions from gas heated to millions of degrees. Through them, we saw the violent, energetic side of the galaxy, impossible to detect with ordinary telescopes. The most transformative tool for mapping the Milky Way has been astrometry, the precise measurement of star positions and motions. The European Space Agency's Gaia mission, launched in 2013, is charting the positions, distances and movements of more than 1 billion stars. The result is a 3-dimensional map of unprecedented scale and detail. From Earth, we cannot travel to other stars, but by measuring their parallax, their tiny shifts as Earth orbits the Sun, we can determine their distances. Gaia extends this method to vast numbers of stars, building a model of the galaxy as if seen from above. With Gaia, the Milky Way is no longer just a band of light. It is a detailed landscape, with contours, streams and clusters mapped in depth. Spectroscopy adds another layer of exploration. By splitting starlight into its component wavelengths, astronomers learn about the composition, temperature and motion of stars. Dark lines in spectra reveal the elements present, while Doppler shifts show whether a star is moving toward or away from us. This technique allows scientists to study the chemical history of the galaxy, tracing how generations of stars have enriched it with heavy elements. It also reveals stellar streams, the remnants of dwarf galaxies and clusters torn apart by the Milky Way's gravity. From the Earth's surface, we can reconstruct the story of galactic growth, piecing together its mergers and interactions. Radio telescopes also let us listen to pulsars, the rapidly spinning neutron stars that emit beams of radiation. These objects serve as cosmic clocks, their pulses so regular that tiny irregularities reveal gravitational influences. By observing pulsars, astronomers test theories of gravity, detect planets in distant systems, and even attempt to measure ripples in space-time itself. Each pulsar is a marker, a lighthouse in the galaxy, charted from Earth with remarkable precision. Exploring the Milky Way from Earth is not limited to professional observatories. Amateur astronomers contribute too by monitoring variable stars, discovering comets, and mapping features visible with modest telescopes. Citizen science projects invite people worldwide to classify galaxies, identify star clusters, and process data. The galaxy is so vast that exploration is a collective effort, spread across continents, generations, and instruments. Even the naked eye plays a role. Simply by looking at the sky, you see the galaxy directly. The dark lanes are dust clouds, the bright knots are star clusters, the glowing patches are nebulae. Without leaving Earth, anyone can observe the basic structures of the Milky Way. What modern science adds is depth, detail, and context. Telescopes, satellites, and detectors turn those impressions into maps, measurements, and theories. Together, they transform the sky from a mystery into a comprehensible system. Exploration from Earth is limited, of course. We cannot travel to other stars with current technology, not within human lifetimes. But light itself is a messenger. Every photon carries information from where it was emitted. By capturing and analysing light across the spectrum, we turn the galaxy into a laboratory accessible from our own backyard. In a sense, the Milky Way comes to us. Its stars send us signals constantly, and all we need are the tools to interpret them. The next frontier of exploration may come from even more sensitive instruments. Future telescopes will map the galaxy in greater detail, detect planets around distant stars, and probe the faintest structures in the halo. Gravitational wave detectors may one day sense the mergers of black holes and neutron stars across the Milky Way, adding a new way of listening to the galaxy. Already, neutrino detectors buried in ice and water catch ghostly particles from supernovae, offering glimpses of processes invisible to light. The Milky Way is not silent, and from Earth, we are learning to hear its many voices. In the end, exploring the galaxy from Earth is about making the most of our perspective. We are inside the system we study, limited by dust and distance, yet privileged to see it from within. Every star overhead is both an object of study and a neighbour. Every faint glow is a clue. The galaxy is too vast to cross, but not too vast to understand. Light has been travelling for thousands of years to reach us, and by catching it, we map the Milky Way without leaving home. When you step outside on a clear night and lift your gaze, the Milky Way stretches above you, a faint river of light cutting across the darkness. It has always been there, for as long as humans have looked at the sky, for as long as our ancestors wondered where they came from and where they belonged. And as you look at it now, after this long journey through its secrets, you may begin to see it differently, not just as a pattern of stars, not just as a backdrop, but as a home vast beyond imagination, yet still the place where we belong. We have wandered through its arms, traced its spiral shape and glimpsed its hidden heart. We have learned how stars are born, how they live and die, and how their remains are recycled into new generations. We have seen how clusters and satellites surround the disk, how dark matter extends the galaxy's reach, how streams of stars tell the story of past mergers. We have followed the Milky Way's motion through space, and even looked forward to its eventual union with Andromeda. We have traced its edge and discovered that it does not truly end, but blends into the larger universe. And all along, we have explored it from Earth, using nothing more than the light that travels across the void to reach us. In all of this, one theme becomes clear. The Milky Way is alive with motion, with change, with cycles of creation and destruction. It is not a frozen picture, but a story unfolding on timescales so vast that we can only glimpse fragments. Yet even those fragments are enough to show us our place. We are not separate from the galaxy, we are its product. Every atom in our bodies was forged in stars, scattered by explosions, gathered into clouds, and assembled into new systems. We are the galaxy made conscious, able to look back upon itself and ask questions. The Milky Way is our home not only because we live within it, but because we are made of it. When you breathe, the oxygen entering your lungs was once created in a star. When your heart beats, the iron in your blood carries oxygen, an element released by ancient supernovae. The calcium in your bones, the carbon in your cells, the trace elements in your body, all of them were produced in stellar furnaces. To say we are stardust is not poetry, but science. And it is a reminder that our connection to the galaxy is intimate, physical, and unbreakable. Home is often defined by familiarity, by belonging, by continuity. The Milky Way may seem too vast, too abstract to feel like home, but in truth, it is the only home we have ever had. Earth orbits the Sun orbits the galaxy. Our planet is part of this system as surely as a house is part of a neighbourhood. We may never visit the farthest reaches of the Milky Way, but we are tied to them all the same. The galaxy holds us in its gravity, carries us in its motion, and sustains us with its cycles. To belong to it is not a choice but a fact. Thinking of the Milky Way as home also changes how we see the night sky. The stars are no longer distant, isolated lights. They are neighbours, each with its own story, each connected to the larger whole. Some are young, just igniting. Some are ancient, fading slowly. Some are remnants of galaxies long since merged. Together, they are the fabric of our surroundings. To look at the Milky Way is to look at the community we live in, even if that community stretches for 100,000 light years. Home is also where stories are told, and the Milky Way has always inspired them. Ancient cultures saw patterns in its glow, rivers, paths, trails of spirits. Today, we tell new stories, written in the language of science, but they're no less wondrous. Instead of gods and heroes, we speak of gravity and fusion, of nebulae and black holes. Yet the impulse is the same, to look at the stars and find meaning, to connect our brief lives to something larger. The galaxy is not just a physical structure, it is also a mirror for our imagination. There is humility in recognizing our scale within the Milky Way. We live on a small planet, orbiting an ordinary star in a spur of one spiral arm in a galaxy of hundreds of billions of stars. From one perspective, that makes us insignificant. From another, It makes us remarkable. Out of all the stars on one tiny world, the universe has produced beings capable of reflection, of curiosity, of wonder. The Milky Way has given rise to life that can look up and see the galaxy itself. That is a form of significance that does not depend on size but on awareness. To call the galaxy home is also to accept its impermanence. The Milky Way as we know it will not last forever. In billions of years it will merge with Andromeda, its spiral arms distorted and lost. Its stars will change, its gas will be consumed, its shape will evolve. Yet its essence will remain, carried forward into a new form. Home, then, is not a fixed place, but a continuity of belonging. Just as Earth changes, just as societies change, so too will the galaxy. But wherever it goes, we will always be of it. Exploring the Milky Way from Earth reminds us that even limited beings can glimpse the vast. We cannot leave our planet easily, and yet we can measure the motions of stars thousands of light years away. We cannot travel to the galactic centre, yet we can detect the pull of Sagittarius A. We cannot touch the halo, yet we can map it through the motions of satellites. Through ingenuity and patience we bring the galaxy closer, turning distant light into knowledge. The Milky Way is not beyond our reach. It is already part of our understanding. And so, at the end of this long journey, we return to where we began, standing under the night sky, looking up. The band of the Milky Way arches overhead, as it has for millennia. But now perhaps it looks different. Now it is not only a blur of stars, but a spiral system with a core, arms, clusters, a halo, and a dark matter scaffold. It is a place of starbirth and death, of collisions and recycling, of mysteries still unsolved. It is the stage for our existence and the source of our atoms. It is not just a galaxy, it is our galaxy. If you let your gaze linger, you may feel a sense of belonging that goes beyond Earth, beyond the solar system, beyond the human scale. You're part of the Milky Way, carried with it through space, bound to it by gravity and matter. The stars above are not just distant objects, they are kin, relatives in a family that stretches across light years. To feel that connection is to feel at home in the truest sense, not only on Earth, not only in the solar system, but in the galaxy itself. And perhaps that is the most important reflection of all, that no matter how vast the Milky Way seems, no matter how overwhelming its numbers and distances, it is not foreign to us. It is the context of our existence, the fabric of our being, the home in which our story unfolds. To look up at the night sky is to look into our own origins, to see the place we belong, to be reminded that we are not separate from the stars, but of them. And as we leave the stars for tonight, remember that the Milky Way will still be waiting above you, whether you see it or not. Its light has been travelling for thousands of years to reach your eyes, carrying stories from distant suns, quiet clouds, and hidden places you may never visit, but which will always be part of you. If you found this journey soothing, you can stay with us for more explorations whenever you'd like. You can subscribe, leave a gentle note, or simply return the next time you want company among the stars. For now, allow the galaxy to fade into the background of your thoughts, like a lullaby written in light. Let its vastness be your comfort, and let your breathing match the quiet rhythm of space itself. Good night, and sleep well in your home among the stars.